some of y'all have been entering these little forms at our booth at the Edis Research table to win this USRP into 10, about a $3,000 value. And I decided to do it live right now up here on stage. I know some of y'all, I said I was going to do it yesterday at lunch, but you know, I've taken all the cards that are in here, I've randomized them and shuffled the deck. Let me hold that for, you know, this is Priyanka. Say hello, Priyanka.
Hey everybody.
Anyway, so we're just gonna give away a radio. That's all I got for you. That's all right. So Priyanka, go ahead and draw randomly. Don't look. Let's see. Hopefully this person is here. Let's see. Ethan Hetrick from ASU. Oh man, Arizona State University. The grad students or undergrad students probably don't get up this early, right? Is that what's going on here? Still asleep. All right. Well, if anyone sees Ethan, tell him he's the proud owner of a USRP into 10 or an NI 2920. We like to have multiple model numbers. And with that, you know, I will hand it off to Mr. Derek Cozell to start us off for the day. Thank you very much. Do you know, is Ethan with Dr. Bliss?
I'll find out.
Okay. Well, he's here, so locally.
Do we have any slides for the morning? Do you know? We do. Grand. These are even them. Wonderful. So welcome back to the 4th day of the GNU Radio conference. Predictably, the room's slightly more empty at 9 a.m. than it was on previous days. Everyone, I hope, had a really good and enjoyable evening. If you didn't, we haven't heard about it and we don't want to hear about it. So, you know, keep it to yourselves and sleep in. But we do continue on with the track today. So we do have the hands-on day tomorrow where we'll be doing interactive discussions about GR4. We have some folks who are going to be kind of available for GNU Radio Q&A questions about specific applications or questions about how to do stuff. And then we'll have the capture the flag session where we'll go through the solutions to a whole bunch of the challenges. So that's an opportunity to see how different techniques can be applied to solve different real-world problems. Today, we continue to get warmer and warmer. Thankfully, in here, we appear to not be getting colder and colder, which I think we can all appreciate. So comfortable in here, wear your sunscreen, drink your water in here anyways, but drink extra water when you're outside. The expo hall is wrapping up. I think by now, as several of the exhibitors have said to me, anyone who wanted to see this has probably already come by and seen this, particularly if you like eating. So do drop by and ask any last questions you have. They'll be wrapping up. I've already seen a couple of them taking down their booths. So kind of by lunch and certainly by the PM break, it will all be closed up. We do have 2 workshops today. One of them, this timing has been, I think, slightly adjusted, but just after the AM break, whenever that happens, will be the GR4 block workshop. So that'll be the panel that we have coming up will be a chance to ask questions in a kind of a broad sense, and then that workshop will be a chance to really see this applied and ask in-depth questions as well as tomorrow. And then introductions to GNU Radio with Python. Wiley Standage-Beyer will be presenting Introduction to GNU Radio with Python. This is a really fun workshop where you strip off basically all the top layers of GNU Radio and you say, given just Python and a text editor, can I create an entire GNU Radio flow graph line by line? And it turns out that's not all that many lines, including the blocks, and you can get a useful result out at the end. And that's a really fun way of seeing just how simple this can be when it comes to the code. The main track talks continue through till about 4:30. Friday is where we put in the most wiggle room to let everything else from the rest of the week kind of shake out. So, plus minus 15 minutes. But we'll definitely get out before 5 o'clock today. I think everyone here knows the Wi-Fi and speakers as well. And I'll apply this retroactively. I think that we have almost everybody's slides, but there's been a few people who have used their computers. We'll chase you down in person if you don't submit us something for the archive. And we do have a couple of slots open today, particularly if I don't get my lightning talk slides put together by the break. So stop by the registration desk if you have anything you want to show off or questions you want to pose. The chat server, this continues active year-round. We don't roll over the server or anything like that, so join and continue after the event. And that's the end here. I apologize, I'm a little bit ill-prepared. I know that our next talk is about using GNU Radio to receive faxes, but I apologize, I don't know who the speaker is. So if you can come up, we'll get you started. Wonderful. I'm glad that they know who they are. Or do you have somebody else's slide deck and you're just presenting it ad hoc? No, Matt, great. So yes, welcoming Matt to the stage. Thank you very much, and carry it away.
I'm Matthew DeMorat. I'm with Oak Ridge National Laboratory, and this is a personal project that I put together about receiving faxes with GNU Radio. So specifically weather fax. So weather fax is a system that was designed to send weather to ships when they're out to sea, because before the internet and stuff, you would need to know the weather so you didn't crash or into like fog or stuff like that. So they have locations around the world where they broadcast and you can receive on your ship and print it out. So it uses radio facsimile or fax. So radio facsimile was invented in the 1900s, and basically the early systems use a rotating drum and a pen plotter to print images. And so there's two main frequencies, one for the black pixels and one for the white pixels. And usually they go 120 lines per minute or 2 lines per second. And so here's a picture of an old fax machine. And so this is the hardware setup that I used. I used an LNA and an up converter because it's HF frequency to an RTL SDR, and then to my laptop. And so the first thing I needed to do was to make an antenna. So it's HF, so I couldn't use, I looked at doing a dipole, but that would be very large, or a long wire or random wire. So I eventually decided to do a magnetic loop. And so here's a diagram of the first antenna I built. So I 3D printed a variable capacitor that I made, and so that seemed to work. On the picture on the left, you can see the low capacitance, like 100 picofarads, and then moving it, you can get to like a couple hundred picofarads. And here's the 3D printed antenna. So I just designed circles. So there's the inner loop and the outer loop, and those are all just made of coax, and you can see the capacitor on the top. And so that didn't work very well because I didn't have an antenna tuner, and I couldn't, without any equipment, I didn't know what frequency I was setting with the variable capacitor. So I ended up just going for just a U. It's called the U loop is what I based it on. So it just has a one-to-one balun and basically a loop of coax. And so here's the balun that I wrapped out of an old TV balun that I just took the core out and rewound it. And then I'm not sure if it helped, but the design for this antenna has like a crossover. So just you change the inner conductor to the outer conductor, and that's something that I added to the top. And here's a picture of it. And for the up converter, I used the new elec up converter, which just basically multiplies by everything up by 100 megahertz, so I could actually pick it up, because the direct sampling on the RTL SDR was not good enough to get a good signal. And so this is the SDR I used, just the RTL SDR. And so here's a picture in GQRX of the signal. So it's at, you can see that it's SSB suppressed carrier. And so I decoded that using the Weaver demodulation so I could get the audio out so I could test it against known fax decoding methods. So here's a block diagram. And basically, I need to shift down the entire signal to a lower frequency and then demodulate with the Weaver by multiplying the real and imaginary parts. And here's what it looks like in GNU Radio. So I have the input here, and then going towards the Weaver block, and then as an audio output. And then we come to the actual fax decoding. So it uses automatic picture transmission, or APT, which is the same format that the NOAA satellites use, if anyone's familiar with those. So it just sends each pixel one at a time, and takes about half a second per line. And so, like I said earlier, there's two main tones, 2400 for the white pixels and 1500 for the black pixels. And for this, I just have the single sideband signal going into a translating filter because I just wanted to center for the quadrature demodulation, and then printing it out to a display. And so here's a picture of the translating, and here's the GNU Radio block diagram for it. And to make this whole thing work in GNU Radio, I use the time raster sync just as like a printer, basically. So everything would print out in the GUI. Here's some images that I decoded, so you can see the United States over here, and then here's Europe. I don't know if you guys can see my mouse or not, but you can kind of see. And then I'll show a video. So here you can hear the two tones going back and forth, and then the printout. And to actually align the image, so there's this black bar, which is the align. I just used a delay, so a time delay. So I'll just go ahead and realign it, and you can see the NOAA symbol up here in the top. And you can see the Great Lakes coming up in the middle. Yeah, I can keep it running. Were there anyone had any questions?
Hold on one sec. Let me get the mic.
So is this system currently in use still?
Yes, so this system is currently in use, so you can go on and get a signal anytime. So there's certain intervals. So that was one of the hard things during testing is I had to wait for a transmit time. So there's on the NOAA website, you can log in and see what times they're transmitting, and then it takes a long time to get the actual data. So I think it's about maybe like 10 minutes per map. So this one will keep going. I don't know if I have the complete recording.
And the numbers that are on the map, that corresponds to some kind of weather?
I believe these are like wave height graphs. So there's different ones. Like you get ones for like temperature, wave height, tides, or this might be a tidal chart. I can't remember which one I decoded, but there's and depending on the year, they have ice charts and that kind of stuff.
Last question. How similar is this to like a regular telephone fax machine?
I think it's like a very similar concept to the early ones. So in the beginning of like the facsimile and fax, they actually use just like your radio that you would have in your house, and then you hook this up. And that's why it's using AFSK in the audio frequency. But I think later on they changed the modulation to something different.
Hi, can you tell me what's the baud rate?
Not sure. I think it's. I'd have to look that up. I don't remember.
Did you create a transmitter flow graph as well?
I did not.
Okay.
I was hoping you could tell me a little bit more about the 3D printing of capacitors, of variable capacitors.
Okay. So I just designed basically like a parallel plate, and then with a slot in it, so it would just slide back and forth, and I could continuously variable the capacitance.
Okay, did you use like a conductive plastic or
I just
alloy
used,
or?
I just used conductive like tape, like aluminum tape or copper tape.
Okay.
Would work.
And then I had one other question. I saw you were using a quadrature demodulator to differentiate between the two tones. Did you consider or try using matched filters? And is there a reason, like a matched filter for each tone and then comparing?
That's the way I just ended up doing it.
Okay.
I immediately got the 1s and 0 from the quadrature demod, so it was easier to put it into the raster sync. But I'll have to look at it.
I was just curious if you'd tried that or not. I don't know if it would be better or worse.
This is less a question and a statement. As a credit to how easy it is, or can be how easy it is to learn and use GNU Radio, this presentation was presented when Matthew applied to come work at ORNL, and we had put GNU Radio in our requisite, our advertisement for the job, and he did not know GNU Radio. So to prove that he could handle it, he went out, taught himself GNU Radio, built the antennas, and presented this to us within 2 weeks. So congrats to that.
Thank you.
Any other questions?
Just say, GNU Radio may be easy, but I mean, honestly, Matt, it's like really awesome that you were able to do something like that in 2 weeks. I don't know if I could do that, but it was great work.
Thank you.
Thank you very much, Matt. So the next item up on our list is to run a panel discussion about GNU Radio 4.0. So bear with us for a moment while we get everyone up on the stage with some seats, but we'll be just a moment. And please do start thinking of questions.
Test.
Yes, please provide evidence supporting you being on stage. No. Everyone here has already certainly done so, although we'll start with introductions. Not that probably pretty much anybody on stage needs one, but it's nice to have it as a coherent whole. Yeah, we ended up with an extra chair. Great. I might get to sit down. Oh, no, wonderful. This is good. Now we get to ask the deep C++ questions. So great. Welcome to the panel, talking about GNU Radio 4.0. This is, in many ways, an opportunity to interview and discuss with people who have been most active in the GNU Radio architecture team over the past year. There are people who are not here, unfortunately, who have been jumping in and out of the conversations remotely, particularly people at FAIR who couldn't travel over in bulk, but hopefully we'll be able to have some more discussions. And I don't know if we've set the date for the next architecture. We have not. Soon. We'll have one.
So my recommendation.
Microphone?
So yes, to join the architecture chat, which this is generally a subset of folks that are involved in that, on the Matrix chat, chat.gnuradio.org, there's an architecture room, #architecture. So join there, and that's where you get the information about the next chat. So sorry, Derek.
No. So that's how we can join, and they're both held as asynchronous conversations in chat. There have been some emails bouncing around, certainly, when longer form discussion is needed, and then when you really just want to hash out a concept, we do semi-regular calls, video calls. And so please feel free to drop in on any of those and contribute. So let's start down from the end, just with a quick introduction of who you are, and particularly in the context of why you would end up on the panel here.
Jeff Long, the GNU Radio 3.x maintainer, and so my interest is keeping the transition to 4.0 smooth when it happens, and understanding how we're going to maintain blocks across the versions.
Thanks. So I'm Markus Müller. I used to be the maintainer like 2.5 years ago. So I'm still trying to get a bit of a picture in my head and contribute.
Yeah, Alexander Grimm. I'm working at FAIR, and in that capacity, I'm working on some of the aspects of this graph prototype that will hopefully soon be merged into GNU Radio Dev 4 branch and then become the new GNU Radio 4.
And I'm Josh Morman. So I've been involved the last couple of years, various aspects of maintenance and the iterations that have been on this path to GR 4.0 up to this point.
I'm John Saleh, and I talk a lot about PMTs, and I've been working a lot, FAIR's been doing most of the work, but helping to make sure that everything interacts well as we move forward.
Hello, I'm Ross Steinhang. I work for FAIR. And if everything is good, that are these guys. If something is wrong, that's me. So you can ask me stuff about what could be better.
How broadly can we apply that to, if the food's bad, is that your fault? So I wanted to start with a bit of a reflection. I mean, the fact that we're all here in this conference now, an opinion that I hear fairly often is that GNU Radio 3.10 and even 3.6, 3.8, 3.9 are good enough for your application. So what would you point out towards some of the strengths of GNU Radio, of these various 3.x versions, hopefully 7 and above, that are properties that you think are intrinsic? Like, what makes it GNU Radio in your mind? Starting with anybody who would like to.
Okay, since I already have the microphone, obviously, like, what GNU Radio is you take a block, you connect it, and then you hit run, and it runs, right? So the two main things are blocks and that you can connect them. And to be fair, like it wouldn't be GNU Radio if this was LabVIEW, which, allows to do the same, and Simulink does the same, but it's very easy to actually write a block, go in there and do something. And so this is a very core idea that you can give anyone who has like this engineering or this technical or this tinkerer approach to things. I do this and then I do that, and then the result is this. You can very nicely represent as a chain of blocks.
It's also a community, a bunch of online resources, the OOTs you can find around, and applications like GQRX that you can find various places. So kind of broader than just us.
I'll also mention accessibility. I've used a handful of other signal processing frameworks, and it is really nice that GNU Radio, like, you need some sort of RF background of knowing what a spectrum nominally represents. But GRC is a really valuable tool for people, and you don't have to have a bachelor's or a master's degree in engineering to be able to use it and do useful things. And that's a really powerful feature of GNU Radio.
And I'll add on to that in terms of accessibility, that there's varying levels of accessibility. So you can just string blocks together in GRC and make something work instantly. You can make little Python blocks in GRC without even leaving GRC. And then all the way down to you can make very complex C++, hardware accelerated blocks if you'd like to. So the gamut of where people are able to fit GNU Radio into their processing workflow is pretty diverse.
Don't forget, I think we have Fortran hiding out in one corner
it is.
of code somewhere. Yes. So those are some of the pieces of what makes GNU Radio, and I would certainly agree with many of those there. In addition to it being an open source project and as you say, community developed, I think it's a really good point to say that the ecosystem is an important part of GNU Radio. And when we say, oh, we're going to rewrite the code base and we're going to break everyone's blocks, everyone's flow graphs, that's a dramatic statement. And if we're saying that ecosystem is an important part of GNU Radio, then that transition is really going to be a key part of what makes this possible to call 4.0 GNU Radio. If nobody can make that hop, then we should really rebrand and say this is, we have old radio and new radio. So what do you think some of the weaknesses are? Why do we want to go to 4.0? If that transition is going to be hard to develop and hard to jump, or at least work to do so, what makes it worth the while? You can't voluntold somebody to speak.
Yeah, so as much as we've worked on GNU Radio 3, it's got some stuff that's fairly difficult in it for anybody who's tried to understand history and forecast and a bunch of other things, and tried to get really good performance and low latency out of it. So yes, we can explore signal processing, put together some projects fairly quickly, but what we want to be able to do is have you be able to use GNU Radio all the way into your final product, and that's where we fade off a little bit now.
Yeah, absolutely. There's just a lot of design decisions that were made that might have made a lot of sense back in the day, but were grandfathered in, and Ralph went into that bit. There were things that I can't simply explain, right? And there are things that I would say were architecturally not a good decision, but given the programming tools and the knowledge of the community at the time were understandably done. For example, everything you handle in a GNU Radio, using application is typically a shared pointer, which is a great thing if you actually share that pointer with multiple threads, multiple consumers need to ref count, but it's usually not a good architecture if someone actually knows who owns a block. It should be some specific thing and not something that at some point might disappear or not disappear if it's held by Python or not. So there's a lot of architectural things that I wish we could solve in the 3 series, But the moment we actually go in there and solve that, we're changing the API very fundamentally, and then we might as well, fix another couple of things on the go.
Yeah, so last year when I was at GRcon, I did kind of an informal polls. I met various people, and I asked, are you using GNU Radio for prototyping, for production, or both? And one person said that they had one really oddball application that they were using in production, but pretty universally people said, we are using this for prototyping, and then we go and we handwrite everything into the production code. And so FAIR is doing a really good job of thinking of how can we close that gap and make it really easy to go from prototype to performant, secure, and usable, maintainable production code.
As a quick poll here, if people could throw up hands, who is using GNU Radio in a deployed application, in something where you would say, maybe it's not a sold product, but it's a developed system that you consider as the final piece of that system? Okay, yeah, that's reassuring that there are some hands, but unsurprising that it's not the entire room. So that, for folks on the web stream, was probably 15% of the room, 10-15% of the room. So good, and let's get that number up in a couple of years. So I want to ask, are there any questions from the audience at this point? We'll jump back onto some other prepared ones, but we have lots of technical pieces and that we saw yesterday and lots of theory that we've talked about. What questions do folks have?
So first of all, I do have a roaming lavalier to help with questions, if you wouldn't mind waiting for that. But I do have a question. So for all the people on the stage, can you raise your hand if you're, as you know, working on 4.0, you're focusing or you have a lot of focus on usability? Okay. So, and ease of use. Could you give some examples, like, brief examples of what it is that you're doing to make sure that it continues to be usable for those of us who don't necessarily want to code, or I think the great example of not necessarily needing a bachelor's or master's.
I think about, and I want to echo again, because it was like a very important message that Jeff made. This is about the community. This is about you. And we want to preserve what is good about it, especially what is the UI interaction and stringing of graphs. How I consider this is a bit like a house. If anybody of you is a house owner, like you build a house, but every now and then you need to do some maintenance. You have to exchange the gutter, you have to exchange some paint, and sometimes you have to do a bit more changes because some bars rot away. And that what we just did is the house, which we all use and we're happy with, works well. But it's still a continuous commitment to renew it and make sure that it also worthwhile for the next, not just the next 5 or 10 years, but that we have an easy maintenance, that we not just say like, okay, this is like beyond help. We have to throw everything away and always start from zero again, and that this happens again every 5 or 6 years. We want to bring GNU Radio in a way that we can make incremental changes which are easy, transparent, where nobody says like, oh, I don't want to change this because I would have to change the whole code bases, where people feel comfortable maintaining and using it. And in terms of usability, from the graphical concept, ideally people who just use the UI shouldn't see no difference. That should be identical. Most of the stuff that we change is under the hood. If you're a block developer, this should be significantly simpler because you just have one single place where you have to write your block. The single source of truth is the few 10 lines of code you need to write. What I showed in the slides yesterday, that's not like slideware where it's like, oh, I took just the conceptual things. This is full production code. So what took earlier like hundreds or 200 lines of code to write a simple block is now literally 6 or 7 lines. And that is helpful, even in very simple C-style lines where you don't have to know too much about programming. You can just say like, okay, that's a function signature. This is my input sample. And I know this return statement, I have to put my output sample. And then the rest is basic math that everybody can do. And that is fundamentally important that even if you don't know the GNU Radio ecosystem, and you want to write a blog, you don't have to read a lot of documentation because most of the things will be obvious because of the block structure as it is. So it should be intuitive. And that took some time. And there we also need your feedback, because in terms of naming, to see like what we showed yesterday, is it intuitive? Or you say like, oh, that's a concept, you need documentation. And for me, it's always the more documentation you need for a concept to explain, that shows me also there's a deficiency in the design. You have to reiterate and make it better. So that basically, somewhat freshmen from university within the first week can hit the ground running.
So we've got does anyone else particularly want to respond? No. Let's go to the next question then. And let's not stack the deck too heavily. We've also got a question down at the front.
So I'm actually relaying a question from the internet, specifically from Barry, whom we all know and respect, and he asks, how will 4.0 affect documentation such as the wiki? And I'm going to add a little thing myself. Ralph, maybe you can comment on the way that inline annotations will affect documentation as well.
That's a big thing. I hope. I mean, like, we have to preserve what is there, because there's like a lot of institutional knowledge. I think in terms of the general usage documentation, most of this applies one-to-one. Maybe obviously like the low-level API is different, but I think what we did is with this inline code documentation should making writing blocks easier. So you don't have 2 or 3 places where you need to maintain code, but just documentation, but just one. For the transition, we have to see with the wiki specifically how we make it clear. Now you're looking for documentation for 3.10, and what is the documentation for 4.0. So maybe we have to add like a bar, like some visual indicator. This is like the existing production code, and then in one color with a bar, and the other one is 4.0 with a hint, depending on which version you use, that there might be some documentation that is different for either.
Yeah, I'd like to add to that we already do have the capability in the wiki to say this applies to version 3.7, 3.8, or 3.10 specifically. We can just extend that, like just saying this applies to 4.0. That is certainly possible. The good thing with our wiki is that, you know, this is all our infrastructure. So if we decide that for now we need to have like, we migrate all the block documentation to say a different domain and say this is the docs.gnuradio.org domain, for example, and we have the block documentation there and a specific wiki that might actually be a new one, we can do that. So I'm not a fan of splitting documentation because it gets out of sync, and we had a very nice discussion on the docs channel on the GNU Radio chat server. So, you know, obviously I'm advertising this now. There's a docs channel, #docs on the GNU Radio chat server. If you're into, you know, improving documentation, if you have questions about the documentation, rather about the thing that is documented, then that would be a great, you know, we'd love to see you. It's very hard to actually good technical writers to get people to proofread documentation, and that's hard enough. So I'd say probably this is, you know, not something that I can enforce or want to enforce, but I foresee that the wiki is not going away. We're going to be better about marking which is which and which applies to which version. And I think also this might be something that we put, you know, specific effort into, is linking the API generated docs, so something that our compiler and build infrastructure spits out, better to the documentation that is in the wiki and vice versa. That is very reasonable to do. There is some kind of difference in what you would write into a block doc instead of a wiki page, and I think it would be good if we had some guidelines on how to do that for all developers and all documenters to apply.
I want to put out as a milestone for us for 4.0 or maybe 4.01 that every block should have an example flow graph, and also to point out that and acknowledge and thank that ARDC has actually funded testing all of our existing example flow graphs and doing documentation work. So thank you to them, and hopefully that'll be feeding fuel into this effort and letting us make some of the jumps that have an energy state level just a little bit beyond what we seem to reach in our resting state.
So I maintain some OOT blocks, and when I first started it took me a long time to figure out how to do some things, even though the code was right in front of me. Like, for example, if you want to add a variable to a block, I needed to modify the YAML, modify the overall header file, modify my header file, and modify my code. And it took me quite a while to figure out that I needed to do all those things, and even though I was getting errors at various places. So is 4.0 going to fix that, or is it, because the way you described it yesterday was all you got to do is put code here. Well, how are you adding new variables and things like that?
Aye. Why don't we spread this around?
Oh yeah, so
one more, sorry.
So that's been in this path to where we're at with 4.0. That's been a common theme of it's been a common complaint, and having that single source of truth that Ralph talked about is the direction we've gone. That you put what you need in one spot, and then there's no point. There should be no reason for a person to have to go and do all that boilerplate manually. It drives people away from GNU Radio. I've worked with people through the years. They're like, I don't want to do this with GNU Radio. I'm doing this little bit of DSP. I'm just going to go, write whatever my own C++ code. So we want people building things that can fit into an accessible framework that's available for everyone. So that is definitely a theme.
So that was a property in NewSCED a couple of years ago. One of your core goals was the code reorganization and having a single source of truth. So
that's being carried forward.
Yeah, and so specifically for the mechanics of that, say all the parameters to your block are stored as, is it a vector of PMTs? Okay. But there's, the constructor takes the PMTs, is that right? Or did that change?
Exactly.
Yeah, go ahead.
Maybe I should. No, it's better. I make some advertisement for John, because it was like was instrumental to change that. Like for the low-level block writing, if you need a variable, you just declare your float, and then due to the power of compile time reflection, you automatically see that field, and when you call the constructor, you use these are automatically translated to PMT maps. So you have a key and PMT, and then it's all done for you. So if as a block developer, you start with a struct with your name. You say this struct derives from the CRTP template. This is think of it like a std vector where you just have to add your type into this. You say you define your input port is like one line, your output port, and then all the variables and the types that you would need for if you're a C++ developer, and the rest will automatically generate the settings initialization.
That modifies the YAML also, so
you don't need a YAML anymore.
Oh, okay.
So basically, it's only this 10 lines of code. Everything is handled, and the beauty of that is because my experience was code generation is nice when you start writing it, and for the guy who wrote this code generation, but after some point of time, maintaining the code generator gets boring, tedious, and then people move on. And then if you inherit such thing, it's always awful. This doesn't happen in the first 3 years. This happens after 5 or 6, 7 years. And we had like 3, 4 different projects where we had this. So I said, like, if we can get by without code generation, all future maintainers will thank us for that. So we said, like, can we do it without? And compile time reflection, which we now still have a library that helps us with this, but is core feature, will become a core feature of C++.
Just a moment. Would it be possible to get the clock back up on the rear of the panel, the rear of the wall? Thank you.
And does anybody else on the panel have an idea how this would integrate with GRC or whatever the future of GRC is? Would that use the introspection to figure out how to make the GUI representation of block parameters?
If you put the annotation in, the UI can derive everything from the annotation. We have some helper methods where you can say, like what I showed yesterday, you have a helper method that inspects the struct and generates whatever. I mean, you could generate a YAML file from that. You could generate a PMT map that tells you, like, okay, these are the variable names with these types. You also can get, if you annotate your fields, get the description of the fields. So you can make like markdown descriptions that you can use in your UI to say, like, to replicate the wiki. I mean, like, concerning for the wiki, there's a part which you can take directly one-to-one the code documentation and inject into the wiki. Maybe even like the examples could be also added to the code. Then the question is more, how big you put the documentation in the code, or whether you say like certain examples you want to live just in the wiki, not in the code base. But I hope it should be, yeah, much simpler. But this is always like here, if that's often like when you present something yourself, you think for yourself, oh, that's way simpler. But you guys, have a look at it. You're the judge of whether it's easy or not. And so we're at the stage where we invite you to have a look at it, experiment with that. Be aware that's presently not a feature complete. No, we didn't import all the blocks that are there. So we just implemented the hard to implement bits, the MVP bits, so that you can string up already meaningful flow graphs to try this out. And then, yeah, see whether you have feedbacks. And we will still have, like, this is not like a once done, never change. This is a continuous process, continuous improvement, continuous change for the better, where you're part of and you're instrumental as well.
As a second question, I've had 3.10 has solved the install problems I've seen in all the previous releases. I've kind of given up installing all the other versions, and especially building from source. And in 4.0, are you carrying that forward? Are you thinking about what it takes to install it on every known platform known to man?
So I'll jump in with a leading piece here. Again, thank you, ARDC. We have a significant chunk of money, I mean, like over $60,000 to address installation pieces. And as a call out to Ryan Voltz and others who do the packaging, 3.10 has definitely been much better than the past. So much better that we're not perfect, but we're so much better on 3.10 that there's actually a question standing whether we should redirect that ARDC grant to 4.0 to make sure that out of the box we're absolutely nailing it. There are already plans for it to be better than it has been, but I'll pass that to the panel if anybody would like to add pieces. But
Derek mentioned Ryan Voltz, and he's really to praise for that. He wrote, he maintains, this is an ongoing effort, it's something that you do every day, the Radioconda environment, which is basically a set of recipes that set up an Anaconda environment. If that doesn't tell you anything, it just says you can download an installer for your favorite platform, double click, and it will set up, it will come with its own Python, it comes with all the radio libraries, and then for some important OOTs, it also has installers. So this, I wouldn't say that is a solved problem, because the problem is, easy problems are quickly solved, and the real problems are when you then need to deploy that, say, in the company network or something. This is not a solved problem, but what we can do basically is make the software easier to install by not being absurd about its dependencies, and I think we're doing a pretty good job in the last couple of years about that. And that's also like, I remember the 3.7 to 3.8 transition. That, we got a lot of headwind, understandably, from people that used GNU Radio 3.7 and were very dependent on that continuing to work. And we were like very sorry, but we could not support, we couldn't develop 3.7 forever because it was depending on things that simply died out, like Python 2, Cheetah, and other components that simply were not feasible, literally not possible to supply. And when you redesign a software and write it from scratch, you get to choose what you depend on. So obviously we're not starting with, yes, this is the full boost installation that you need to build this. And that makes things a fair bit easier, but it is an ongoing effort. And I know, Josh, you would probably agree if someone says, hey, I have this cool new feature that I want, but it makes us depend on libverycool, and libverycool only exists for Windows 3.11 and Linux 2.6, then it's not going to end up in tree. So that is something that we can ensure, but it's not very much an architectural problem. It's more a maintenance, environment, talking to people problem. Right? This is very much a communicative problem, because hard to install is always, someone made it run on their machine. So in absence of the opportunity to ship their machine to everyone who wants to use it, yeah, it's just about communicating what is an appropriate way to make things work. Well, usually we're getting better about that.
Yeah, And so, I mean, Ralph, do you have comment on the portability, the lack of dependencies in the graph prototype?
Yeah, that's maybe I'm. I would just want to say I'm a dependency Nazi, because I said, like, for me, zero dependency is the best dependency. There were some dependency that we couldn't avoid. For example, we wanted to use FMT formatting library. We accepted that, just to give you an idea, because we knew this will become or is now part of the C++ standard. We just used it as an intermediate dependency because not yet all compilers supported that out of the box. This will be one of the first that we drop. And the other big dependency that we have inside, but which we could incorporate, is FFTW. For every dependency we put in, you have always to make a trade-off. How much benefit does it give you, and what type of maintenance nightmare it gives? And if in doubt, we rather choose, because a library on the low-level end should ideally not depend on anything other that is higher level. We had the problem with the boost, also in our facility, where you had different libraries having different versions of boosts. And if you want to link them together, that's a nightmare. And we never want to go back to those type of problems. So the idea is that the core, the lower you are, the less dependency you have. So the core library will ideally have no dependency, with maybe the exception of FFTW, because rolling your own, I mean, we wrote also our own FFT implementation, but this 50% performance boost, I thought, like, I don't want to give up performance on that. So they made an exception. The second thing that we made for portability was we aimed at both compatibility with GCC, Clang, and MSVC. We have some collaborators that also compile it natively to Microsoft and Mac, and we hope that this will help for the packagers to have the same less if-else if you're on this platform or that platform. And the third ingredient is it's largely header only, so you don't need to package necessarily. If you say you just use compile time graphs, there's still a SO dependencies if you want to use it for GRC and have a compile time, runtime connectable graphs, then you need an SO. But otherwise, we're very aware about that. And that's our contribution also as a large scale deployment, because we have hundreds of those, and having heterogeneous dependencies is a nightmare.
And to add to that, we do need to be a bit self-critical there, and I think we fairly are. It's that we do have a dependency, right? It is a modern C++ compiler, which is, that's a steep call to make if you're trying to compile for Zync in specific circumstances. But that's the thing, right? We're not developing the software for end of 2023. We're developing the software for end of 2023 and the 16 years after. So that is, you have to go a bit forward in dependencies, just to be sure that in a year you're not regretting what you're doing now. That's the one thing. And you mentioned that 3.10 solves the installation problem, and I thought, like, where does that come from? And one hand is like RadioConda by Ryan Walls, and the other thing is probably that, through RadioConda we got all this CI that actually builds on macOS and on Windows, and we do catch bugs. We actually caught a lot of bugs when we introduced that we didn't see in our continuous integration tests every time we made a code change before. And because a lot of us, don't actually work on every platform, it took some time before to detect that. And if you knew GNU Radio before we had the CI running, you knew that bugs could, be in there for a while if no tests are run against them. So that might be the reason why we're getting better at this. And Fair certainly doesn't write much software that they don't test before they deploy.
Thanks, Marcus. Yeah, just
Yeah, sorry. I was rambling on.
It's not a Stack Overflow answer. So I know we have another question there. We'll get you in just a second. I did want to kind of jump in and insert a question, which is, in terms of user interfaces, there's been some discussion, which I don't think was really covered in previous bits, about the difference between the computing flow and rendering out, a user interface, and whether there should be a different separation. Will we keep using Qt, GRqt GUI, or is there interest in doing something different? Start with Jeff.
Yeah, so we saw some interesting talks earlier, like Luigi's talk, and stuff with web using ZMQ to pipe out to other programs. And I think part of the solution will be making clean interfaces where we don't have to build it all in. Because going back to your question on dependencies, we do depend on Qt. The new video sync that's going to go on and depends on a specific package from Qt. So we don't totally, the core doesn't control all of the dependencies. We still have to be careful of that at the broader project level. But yeah, I think if we can make some standardized ways of transporting data in and out, whether it's shared memory or ZMQ, and make that really easy to use, that'll help with the GUIs too.
Great. Okay. Yeah, let's go to a question.
Yeah. One of the questions I've got on the floor is, can you guys please make good examples? Because 4 is a whole different paradigm, and then I have no idea what to do, and it really helps if I can see an example that I can simply understand, and I start building on that, and that builds the confidence to build the more complicated blocks. So please document it and give us examples, because otherwise we're going to give up and go somewhere else.
Do you have any examples of examples, any that you're thinking of?
Well, one thing that would be really nice is I build RF hardware, and if I have to instantiate a new device, it's hard to do because I have to go and talk down to my hardware. And what I would like to see, if at all possible, something that has a simple socket interface, so I don't have to build a complex interface. I can just get the data in on a simple socket, something that I could implement in an FPGA, for example, like a UDP socket or something, and have, I can give you a stream of int16s or int64s or whatever. Can I get something that can interpret that and bring it in into a flow graph, and likewise have simple controls going back, so I can, if some variable is instantiated, it gets converted to an int16, and I get a variable, like a token value and a variable back into the hardware. It would really help us who do unusual and strange hardware, which have ultimately become new products. So it's just please, we'd like some help.
Yeah, sure. Absolutely, very important point. We try to always have like a full vertical stack integration. That's also the reasons why we have our own UI, just to make sure if we build something that we also can integrate it from the bottom up, also for the driver integration. While we have this, also as part of our unit tests, this is just on a technical level so that we can show it works and that there are no gaps in the technical implementation. And this is like where we need help, where we need like good technical writers. Because most of us that develop that are good C++ developers and library developers. But in order to transit it to also like for the wiki page, we need help for somebody who takes this and forms, let's say, like an educational path where transforms it into something simple. This is my Hello World full stack program, and then makes a gradual, let's say, gradual complexity increase for each of the examples. Most of our examples now have something Hello World, but then the second one, the example has all the rest of the features, which might be overwhelming, and we need to improve on that, having more technical writers and people who experiment and bring also a bit like didactic into that. And yeah, I think that we need help.
Yeah. And
are there any other questions, just so we can run a mic? Okay, great. Already said.
Yeah, and so one thing I'll add to that is, one thing, since we've made this this diversion, not diversion, it's the path to the GSI FAIR code that is the basis for 4.0. The reason you're not seeing that right now, like in the GNU Radio repos, is, a lot of it is the lack of examples. We don't want to say, here's the GR 4.0 code, and then it's not accessible to people, that it's this academic thing, because it is going to be GNU Radio 4.0, but we don't have it to that point yet integrated as something that looks exactly like GNU Radio. So we don't want to lose people in the process there. So just a heads up, that's why it lives right now in the GSI FAIR code base. But once it migrates into the GNU Radio code base, will be structured in a way that you can build flow graphs with it and do very concrete things.
You've already just kind of started answering the question I was about to ask, but Ralph, I know that for you and your team, one of the next steps is to implement the selector block, which was something I had asked for as a nice minimal example of a block that has slightly unusual behavior compared to, just as samples in, samples out on single ports. Also in your presentation, I saw you use quite a few picoscopes as your digitizers. So, at what point do you think you might start implementing support for something like that in the 4.0 and graph prototype? And then more broadly for each person on the panel, what do you think next steps are to get us from where we are today to code being merged into the GNU Radio repository and then eventually winding out to a release?
In the selector block, our project is openly developed. We have a project site with a Kanban board where you can see which are the items to be worked on, which are the pieces that are already implemented, which are the ones that need to be done. And specifically the selector block, that is where Dr. Ivan Kucik, I name him also as doctor like Matthias, because he really deserves the doctorate. And he's developing it, and maybe either today or Monday, this is also in the code base. We plan to transfer this into the regular GR repository, but there were some things where we need to change naming, code formatting to clean up a bit before we present it. You can see it already now, it's not hidden code. But there's some housekeeping that we want to make sure that everything is smooth.
So to answer Derek's question, so these guys have been doing a great job focusing on the C++ foundation and the core of GNU Radio. I'm very excited for when they get the Python bindings in, because then we can start saying, okay, now I'm going to write my Python flow graph or try and pipe it into a GRC-like thing and see where the rubber meets the road there, see what things maybe got overlooked or what improvements are there, and that'll be a great opportunity to really stress it and see how it works for the typical GNU Radio use cases.
So in terms of next steps, once we're able to get this into the GNU Radio repositories, having a clear, well-defined structure of here's where we're going to put blocks, mirroring how they're going to be out of tree, and where it really starts to look like GNU Radio that people can understand and access it. I think that's the next step. I'm very much looking forward to the Python bindings as well, but I think there's also a lot, even with the C++ code base that can be done that we could, I don't think that will be the 4.0 release, but we can go a long way with C++ flow graphs.
Yeah, I'm thinking in a similar direction, because the state of the prototype now is that there was a lot of the problems are solved, but they are solved in the place where we solved them. And now there's this step where we have to get all the blocks into a directory where the blocks live, and make sure that every feature is compatible with the other one, and it doesn't get overwhelming if you use features at the same time. And so once we have that figured out, and this is a little bit hard to do while you're constantly adding new features, because some people are working on a feature, and then if you do this complete refactoring and moving stuff around, that's why this was like on hold for a little bit, but I think we will do this really soon to get it sorted out, and then I think it can be merged pretty soon.
Yeah, I think I do agree with all the above. Basically, we do have a couple of projects that are very forward-facing, where we're still working on 3.10 or the 3 series. We have, what I will do is go over the bug tracker of the last 10 years and figure out which ones, which of these bugs are things that we need to think about in the 4.0 development process. That is the official goal, I guess, a bit. And the other thing we have is that GRcon is currently rewriting GRC, right? And he's gotten pretty far. So there's a Qt rewrite of GRC that has very technical reasons. And we'll need to figure out which front end we want to put, to 4.0. I don't even know whether it's going to be the 3.7 series GRC or whether we, end up finding something else. But either way, we need to figure out which are the takeaways from a couple of years of GNU Radio 3 development that apply. And the other thing, and this is very much like me, is communicating how it's done, right? And I usually take the road of just writing a bunch of mailing list posts, going on Stack Overflow, answering questions, and getting the examples out in the world where people actually then refer to. This is very dangerous because unlike a wiki where I can just, edit it in 2 years when I figure out I was stupid, something that was on a mailing list, the internet does not forget. But on the other hand, it's the only way to actually deliver an example that fits someone's use case and explain, hey, you had this problem, so here's how I, as a GNU Radio 4.0 developer, would have thought about that. That's the only way, is actually going in and doing free consulting, kind of. So, yeah, that is what we're going to do, and it's going to be a lot of work just communicating about how things are to be done or typically are done. As usually, we figure out that there's more than one way to skin cats. My apologies to cats. But yeah, if we don't start discussing this in the public, we will not crystallize this golden way that everyone agrees, is a canonical way of writing something.
As far as milestones, I'll be excited when we can build a full digital receiver, complete with clock sync and data.
Great, thank you all. So we had a question at the back.
Hello. One of the other reasons, in addition to performance, I think why GNU Radio doesn't get adopted for production code is the licensing. And are there any thoughts as to making changes to the licensing, and or maybe just thoughts from the panel on why that concern is wrong?
Maybe I can say for FAIR, this is specifically now the FAIR position. We want to interact with industry and the open source community, because we saw when we put out technology that is freely usable, the tendering process for private companies for working with us is much easier because they can assess better what is the complexity. For that reasons, we choose a liberal license like the LGPL, and this is also our code base we contribute as LGPL, even if it's then relicensed to something else, because we feel it's important that this community and also industry in engagement, and to have it as flexible as possible. But this question is to be have, because maybe you do.
I was smiling at the question there because in the car and last night we were talking about the licensing question, and it's been something that the architecture team has been talking about, and this is certainly not a new one. We just relicensed Volk to LGPL, and that was something that we decided was a really pragmatic answer. It is a standalone library, and the virtue that we really cared about was that if somebody received an application using Volk, that if there had been enhancements made to that Volk library, that those enhancements would be available to the end users. And so for me, that virtue applies to GNU Radio as well, and the LGPL does largely convey that. There are issues for me around out-of-tree modules and how that interacts with the LGPL license and end users, but that's a discussion for the community to have. There's no one person on this panel or the whole panel who can make that decision alone.
Exactly, and I think one point I'd like to drive here is that the kind of from scratch implementation that Ralph and the group at FAIR is donating to this project is coming in as LGPL. So it gives us options we've never had before. So GNU Radio 3 is a GPL v3 code base, and you can't change that. You can't do anything about that. So it is an ongoing discussion that will happen, that we do have the option now to do something differently.
Anyone else on the panel want to bite into this one?
So GNU Radio is a lot of different layers, and we may find that we need to maintain some of the code in the middle layers in order to keep everything from changing, and that code will be GPL. So already, a lot of people don't understand that the GPL just means you provide your code to whoever you give the binary to. And so In a lot of cases, just knowing that solves it. If you're not willing to give out your code, then obviously that's a problem because you're linked against GPL code. So if you're creating a new block that where the only dependency is the 4.0 core, then you will not have that restriction. You can have a proprietary license.
If the core is LGPL.
If the core is LGPL, if the full core is LGPL, and the fact that the FAIR scheduler, is currently LGPL, does not necessarily mean that what we think of as the full core will be LGPL. So, to be determined.
It is a spicy question, but it's one that needs overall discussion and everybody in here. So the workshop and the is that an online question? Okay, great. We'll get to that in a second. That's something that I imagine there's probably a little bit of room to talk about during the workshop today, but a lot of room tomorrow and a lot of room in the architecture chat meetings throughout the year. We're still at least months away from hitting a point where we need an absolute decision, because there will reach a point where there will be GPL code that will be very straightforward or natural to want to include in, and we need to decide if and how those are getting merged and divided as necessary or isolated as necessary. But you're far from alone in being interested in this. Let's go with the online question.
Unfortunately, I don't think it's a very short question, but I'll try. So it's Franco Venturi, I believe. And the question is, after watching yesterday's presentation, it seems to me that there's a significant amount of overlap between the vision of GNU Radio 4.0 and Bastian Blossel's project Future SDR, except for the choice of PL, modern C++ versus Rust. How do these two projects compare? Are you planning to work together with Future SDR and to find some form of synergy, or do you have any other comment to make about this?
Yep, I'll go ahead. So Bastian wrote Future SDR because he was, frankly, kind of tired of the GNU 3.7, 3.x series problems, and he also wanted to practice his Rust. So this is a slightly different motivation, I guess, but he did, show that there's a lot of very cool patterns, and we were sitting in a Hackfest together. He was showing us how he implements some blocks like within minutes that would have taken in GNU Radio 3 half an hour to do. And that was really, really cool. I do advertise and recommend you look at Future SDR just to get to an inspiration what software can also look like. So it's a cool project. It's not, I don't think it's a competitor in the course in the strict sense. There can be more than one SDR project. It's also like run by one guy. So this is a bit different situation on the community thing. And Bastian is part of the architecture chat. He's been a long-term GNU Radio contributor. He's been very influential in a lot of later 3.7, 3.8, 3.9, 3.10 architectural changes that were possible within the GNU Radio 3 series. So I don't think this is a bad thing at all, or we need to think of this as something that might split the community. Quite the opposite is true. Basically, and there's also something very nice about both Rust and the prototype, is that there's nothing stopping us from embedding Rust code into our stuff, or vice versa. We might even plug, and this is I'm very excited about that opportunity. We might be plugging his scheduler into our scheduler framework if it's a cool thing, right? And if that works, I'm fine.
For the scheduler, maybe that's one of the differentiating features. The Future SDR still follows very much the scheduling policy of the 3 series, which is a microservice-style scheduler. For high-performance computing, this doesn't work. So we made a work scheduler, so the scheduler is substantially different, the orthogonal implementation. The block implementation maybe can be shared or make wrapper around, but the low-level scheduling infrastructure is different. And these are like 2 experiments. I mean, like you could say if you just care about schedulers, you have these 2 paradigms. One is like a work scheduler, and the other one is like a microservice, like an OS-style task thread scheduler. and we have to see, like in the field, which one performs better.
I'll put out as well that I've been thinking a lot about allowing developers to create blocks in other languages such as Rust or Go and having those integrate in. And that is one of the topics that I wanted to discuss and get feedback from people on tomorrow at the GRC format workshop, is making sure that we have a format for describing a flow graph that enables blocks to be written in whatever language so that we wouldn't have to go in and do a hack after the fact.
We are at the end of the slot, but I want to go down once more and say and ask for any kind of concluding thoughts or dangling threads that we didn't get to, and tacking in something else. What do you hope will not be in GNU Radio 4.0, but you look at and say, as we're looking at 4.1, there's this feature we're not going to get to, or this language feature that's not available that maybe we can take advantage of in the future. And I'm thinking specifically, Alex, you may have some thoughts there. But please.
I got to pass on that one.
Maybe not.
So I think like we're getting to a very cool thing. When I was young and hopeful, and we were having like a workshop on software radio in Karlsruhe where I studied, I've been talking to to Jonathan Corrigan back then, and he was very excited, and I'm still very excited about fully RPC set up flow graphs that where you can deploy this automatically and stuff. And this is the kind of tooling that you develop over time, which you don't get right on the first thing, that you actually need to know what your user's gonna do. So this is naturally something that comes later, I think. We might have something in the early versions, but I'm pretty sure that will change over time.
So I think that to echo what Marcus said, a lot of the tooling make it easier to create blocks. If we look forward, maybe there's even easier ways of creating blocks than grmod tool or that single source of truth. Add in some natural language processing to create blocks, things like that. But am I off? Yeah, no, I'm good.
Okay. So the thing I'm really excited about that is the potential for new ways of running blocks or flow graphs. So I would love if I'm writing in Python and I'm doing NumPy and SciPy and I want to run a GNU Radio block, I would love to just be able to run that one block and pass in a NumPy array and get a NumPy array out. And that's difficult to do right now. And so that would be a really cool application to run a block outside of a flow graph. And I think that the system that Fair has set up should easily enable applications like that. And so I am excited to see what applications the community can come up with and novel ways of using flow graphs that aren't possible now, but the modularity that they're enabling will allow in the future.
I think for me, GNU Radio is about you. It's about the community. And for me, it's important to have this a fun project where people like to use, where it's intuitive and very high performant. And that should be the driving factor. And it should solve a concrete, specific problem of you without lots of boilerplates or burdens. So I think that's always important. And on the short term, to pick on that, we want to support Python. It's not that we say like, oh, we didn't put it back because we didn't want to, but we wanted to wait because now is also like a very good opportunity to reflect upon how do we want to interact with Python in this ecosystems. Do we want to copy the same paradigms of 3.7, 3.8, 3.9, 3.10? Or do we want to go a new, different, better, more improvement path? From our team, we couldn't drive it because while we use Python, we're not the Python power users with 10 years or more of experience for each developer. That's the reasons why, if you're interested in that, contributing, maybe join the GNU Radio architecture chat and say like, also help us to find like a good path for the larger communities that use Python. I mean, like, bottom line is, if needed, we can replicate the exact identical interface as 3.10. But here's also like an opportunity, not just for the core from C++, but also from a Python point of view or other integrations, Rust, to make an improvement forward.
Great. Thank you all for coming onto the panel, and thank you for the questions. We are running a few minutes late onto the break, so we'll jump straight to that. We'll come back in 10 minutes. It's a slightly late start compared to the schedule, but enough time to get a little bit of tea, some biscuits from the AM break. And please join me in thanking all the panel members and all of the architecture team for their work in the last year. Yeah, sure.
Real quick, anyone interested? The Women Plus Part 2, just meetup thing is going to be in CTF room. We're borrowing it for a bit during the break. Thanks. Over.
Grand. Apologies, it's a 5-minute longer break than I'd anticipated, but the conversations were really good, so here we are. Our next speaker is Barry Duggan. Unfortunately, he's not able to attend in person, but hopefully many of you have interacted with him on chat or benefited from all of his documentation work. In addition to the documentation work, he's been building up example applications and trying to fill in gaps where we have them. And so his talk is on file transfer using BPSK. And this is a remote talk, so we'll be rolling his video. He's been very active in chat, so I'm sure if you have any questions, we'll try and take some of them remotely live if there's time, and then he's available through chat for any other follow-up questions. So thank you very much.
I am Barry Duggan, going to present a file transfer using Packet and BPSK system and sort of describe some of the development of that package. At the end of the BPSK tutorial is this flow graph, and it shows a random source feeding a BPSK modulator, channel model, and then into a clock sync and Costa's loop, traditional BPSK decoding, and then running that through a binary slicer. So at this point, we have a bit stream that is the same as the transmitted stream from the random source. So if we take that random source signal and unpack it into bits and change it to float and delay it, we can compare that signal with the received signal and show that they're the same when the delay is adjusted. And the reason for the delay is all of these blocks through the transmit and receive chain introduce delay. So we have to delay the transmit signal by the same amount to compare the two. And it works. But that is a bit stream. So after that tutorial came out, we started getting questions on Matrix chat where the user would put a file source in place of the random source, pack the bits on the receive side, and feed them into a file sync and say, why didn't that work? Well, there are several reasons it doesn't work. The receive signal is a bit stream. So when you do an unpacked to packed, you can put 8 bits into a byte, but there's no byte alignment for those bits. There's a 1 in 8 chance that you'll get it right. But even if you did, the receiver doesn't have time to synchronize on the signal before the data arrives. So you'd still miss part of the data. So that's not a working solution. So the objectives of my project are to send a file without repeating it, use packet formatting to get the byte alignment, use BPSK, and provide a means for the receiver to synchronize with the BPSK before the file is sent. So there is a tutorial on this package in our wiki. It's called File Transfer Using Packet and BPSK. And there's open code in my repository under GRcon23. So along the way, I wrote another tutorial for packet processing. And in this approach, I had a file source feeding a stream to tag stream. and CRC, protocol formatter, and so forth. The protocol formatter uses a header format default, which includes an access key and packet length key twice. Now the problem with this, it worked, but had to pre-process the input file, because if this input file was not a multiple of the packet length, then the leftover part of the file would be hanging in this stream to tag stream buffer, waiting for the rest of the packet. And this particular one was set up for a packet length of 252. So if I preprocessed this file, I could pad it out to multiples of 252, and this would work, but that's not a very good approach. So I came up with this. I have a embedded Python block, which I will describe in detail in a minute, feeding a CRC, the protocol formatter, same header format default with the access key. And at this point, the output of the CRC32 is the payload. So by combining the header and the payload in a MUX, we get what we want to transmit. Feed that into a BPSK constellation modulator, and then resample the signal to a rate of 768K, which is what I use for all of the modules in my GR control package, and feed that to the transmitter. And then to get a picture of what's going on, take this transmit signal, unpack the bits, change it to float, and feed it to a time sync. Now let's look at the embedded Python block. It takes the place of a file source block, a stream to tagged stream block, and parts of a burst shaper block. So it does the following things. It sends a preamble to allow the receiver to synchronize. It reads the file in packet length chunks and then converts those chunks to base 64, so I can send any file type with no problems. Base 64 produces 4 bytes of output for every 3 bytes of input, and it's in ASCII code. So then I send each base 64 chunk with a revised packet length tag. And then at the end of the file, send a post-file filler to assure that any buffers have been flushed along the way. Let's look a little code here. And this is just snippets of the Python. The preamble consists of a percent sign. These are in decimal. Capital U, which in hex is 55, which gives us alternating 1 and 0 bits, and then followed by a right bracket, which one of these things. And the reason for the choice of the percent sign and the right bracket is those characters do not appear in the base 64 alphabet, so this preamble is easy to sort out when I'm looking through the data. So the code gets the length of this packet and builds a tag. The key is packet length. The value is the length of the packet. And then I create a tag to put into the stream with that key and value, and then advance the index so that the next tag will appear at the right place in the stream. Now this is the part that reads the file. While it's not in the file, it's going to read a chunk into a buffer and then look at the length of that. If the length is 0, then it is the end of file, and I close out this part. And if there's data, convert it to base 64 and then recalculate the length of that chunk. So let's look at the receive side. We receive it at 768K and then convert it down to 48K. And then this is using a symbol sync rather than a polyphase clock sync. And the symbol sync needs a normalized signal. So I added an AGC to make sure that we had a good signal, and feed that into a frequency lock loop band edge detector to do the fine tuning of the signal, because over the air 2 US RPs are not going to have exactly the same frequency. And then the symbol sync, the Costa's loop, traditional BPSK decoding, constellation decoder, differential decoder, and a map. So at this point, this is the received bit stream. The correlate access code is looking for that access code that we put in to the protocol header. When it finds it, then it extracts the packet length and creates a tagged stream for the output. So, and this is bit stream. So we repack those into bytes, which are aligned with the real data. Do a check on the CRC and feed that into a file sync. And then we have 4 GUIs for this. We have a frequency sync, constellation sync, input to the correlate access code, and the output to the correlate access code. And this system always puts the received file into a name output.temp, and I'll show what we do to that later. I'm going to show a simulation of the packet transmit and packet receive. So the packet transmit program sends data to a channel loopback where we can introduce some impairments, and then to the packet receive. So this is 3 separate processes running concurrently. So if we look at the first here, we'll do a channel loopback. And it will allow some impairments like timing offset. So let's put a little of that in there. And some noise. And some frequency offset. So then when we look at the received signal, we can see it converge on the BPSK. So the second process is the receive. And we'll do first we'll remove the output files. So we'll make sure we're starting clean here. And then we'll do the receive. And we've got a frequency plot, a constellation plot, the input to the correlate access code signal, and the output of the correlate access code block. And then we'll start the transmit side. So once I start this, watch over here for the constellation and you'll see it converge. It converges pretty quickly. And this is the data being sent, and then the post-amble filler packets. So it is finished. So we'll kill the transmit. We'll kill the receive. And we can kill the loopback too, for that matter. And let's look at some files here. So the output temp is the received file that we got. So that's the preamble, the data, and the post-amble filler blocks. So we're going to run the strip on the receive side. Oh, first we're going to look at the output with GHEX. So let's do that. Bang. And here are the preamble packets. Up to 64 of them. There's the base 64 data. And there's the post-amble filler packets. And the first one of those has the file name that was transmitted. So now if we run the strip preamble program, it will take away the preamble, the post-amble, and convert the file back to its original form from the base 64. And you can see that we got output.ping from that. And if we click on that, there is our icon. For the over-the-air testing, I'll be using two computers. The Lenovo, which is where we did the simulation test. It will run a packet transmit receive switch, which is a control for the USRP. And then it will run the packet receive. Now the way that works is the USRP is going to transmit at 432.2 megahertz to a fun cube that's plugged into my laptop. And then the laptop will send the received signal over a ZMQ pub and sub link back to the Lenovo. And the reason for this setup is so that all of the GUIs can be on one computer, so I can show you better what's happening. On the laptop, the FunCube flow graph is pretty simple. It's a FunCube dongle Pro Plus feeding a resampler to change the sample rate of the fun cube at 192 kilohertz up to 768 kilohertz, which is what I use for all the modules in my repo. And since it's between two different computers, I have to use a full IP address and using a port number of 49221. Now to do this, I need several different tasks running. So we'll get the first one. Since I don't have a Raspberry Pi running right now, I have a dummy for it because the transmit receive switch needs to control the relays. So what I will do is start this dummy Python program. And then the next task, I'll start the transmit receive switch. And we'll set the receive gain down to nothing because we're not using it, and set the frequency to 432.2 E6, which is in the 70 centimeter band, and that's also an ISM band. So for the receive, let me get this, yeah. Here are the output files from a previous trial run. So I'm going to delete those. And then I'm going to run the packet receive. And like the simulation, I've got the receive signal, the constellation plot, correlate input and correlate output. The fun cube does have a DC spike in it, but it doesn't seem to bother anything. So on the transmit side, before I can actually transmit, I have to switch the switch to the transmit mode. And then I can do packet transmit. Now watch the constellation sync over here when I start to transmit. It converges very quickly. And here's the data going by. And that's the postamble filler. So the file is done. So I'll stop transmitting. Stop the transmitter. Stop the receiver. And then let's go back to the receive. And we have a output.temp. And I won't do the ghex again, but it looks the same as the simulation. So next I'll do a strip preamble. And there's the PNG file. If I click on that, there is the icon. So where do we go from here? It would be nice to integrate the strip preamble so it doesn't have to be done as a separate step. It can either occur in stream or in PDUs. And I'm still working on trying to get that to go. If I captured the file name on the receive side and renamed output.temp, that would be great. And I've looked into adding forward error correction, but haven't done enough experimenting with that to see if that really works. As far as integrating the strip preamble with a PDU, the same receive packet program, flow graph, take the tag stream to PDU and then write an embedded Python block to decode the packet and then put it back into a tag stream and put it into the file sync. So this embedded Python block would strip the preamble, convert the text packets from base 64 back to the original form, and then strip the postamble filler packets. So only the transmitted file would appear in the output file. That would be neat. As far as using forward error correction, I've tried a little bit of it, but haven't done really enough experimenting to see if it is effective in correcting errors. So those are the things that can be done. And so you are certainly welcome to clone the file and do your own work on it or fork it. Thank you.
All right, that was Barry, who is presenting this remotely. And we'd like to thank Barry very much because he has been helping with the conference as in the past, and he's one of our sort of main leads on the documentation. So yeah, big round of applause for Barry for his talk and his work on GNU Radio. And Barry is also on chat, so if you're on the matrix, you can ask him questions about the flow graph and his talk. All right, but we're going to move on. Our next speaker, Libby Burkhardt, you might recognize the name. She already presented on the cardboard box hydrogen line measurement equipment, and we will now be talking about the light cube Cubesat.
Thank you. Can everybody hear me okay? Cool. Yeah, I'm Libby. I'm a fifth-year PhD student here at ASU in the School of Earth and Space Exploration. I talked to you a couple days ago about my astronomy work. Today is kind of my other hat with Cubesat work. There's my clicker. That is not clicking. I was not pushing hard enough. There we go. So the kind of broad picture tagline of this talk is going to be students sending stuff to space. As many of you in the small sat community might know, space missions are becoming more accessible than ever. Cubesats in particular offer opportunities to launch new technology for relatively low cost and low consequence and allow students to get involved in the building and development of space missions. In particular, projects like GNU Radio and SatNogs make support communications easy for beginners. And so I'm going to encourage you not to think about this talk as a new cool thing I did with GNU Radio, but as someone using these tools for the first time. And I'm just going to tell you kind of what was helpful for me and what we did. So my background, I'm not a comms engineer, I'm an astronomer. Usually astronomy is not actively trying to talk to us or prevent itself from being heard. I certainly hope that astronomy is not encrypted, but obviously this depends on your personal views about the universe. And so I just want to talk a little bit about some tools that were useful to me coming from astronomy into comms engineering. This also might end up reading a little bit as a thank you note to Daniel Estevez's GR Satellites project and also SatNogs. They're going to come up a lot here. So I'll do a brief talk about the Interplanetary Lab. So the IPL at ASU is not only a student space lab, but a lot of what it does is student space work. So it's a lab that has a whole bunch of spaceflight testing equipment, the usual stuff like machine shop tools and soldering benches, but also in-house thermal vac testing, a vibe test bed, anechoic chamber, ADCS pointing test bed, all the good stuff. So the IPL has been, I think, in use for a couple years and was largely where LightCube was developed. LightCube itself is an educational mission on two fronts. So kind of the tagline I have here is built by students, operated by anyone. You do have to have a ham radio license. The payload is a xenon flash tube that is triggered by ham radio operators, and it should produce a naked eye visible flash. So you can go out with your ham radio, command the Cubesat to flash, and you'll be able to actually interact with it and see it respond to you with your own eyes. LightCube was launched on April 24th from the ISS, and it operated for just under 24 hours before we had a comms failure. And we were actually able to track down why our comms failed, which was almost as exciting as the Cubesat actually working. Being able to know why it stopped working was particularly, at least like as a secondary thing, very useful. To reiterate some of the stuff on the previous slide, here is the block diagram. I didn't work in particular on the Cubesat design as a whole, so if you have any more specific questions, I can direct you to the right people. But the main things I just want to point out again are these xenon flash tubes that are on the sides of the Cubesat in this particular diagram, as well as the deployable UHF antenna, which was how all our comms were done. The telemetry was one of three types. So on 3 different cadences, the Cubesat transmitted a heartbeat packet, as well as a full telemetry and orientation packet. The uplink commands are over dual tone multi-frequency, so DTMF tones, and the downlink telemetry was audio frequency shift keyed. You can see a high quality LightCube pass on the right over there. That's what our AFSK modulation scheme looks like. Our carrier was 437.175 megahertz, so amateur radio band, and we had a baud rate of 300. And I have the mark in space frequencies there as well for the Bell 103 protocol that was used. Now I'll talk a little bit about SatNogs, which was very critically useful to us. Many of you are probably familiar with the SatNogs project, but it is the Libre Space Foundation Satellite Networked Open Ground Stations project, which provides a network of amateur stations. So they provide tutorials if you want to build your own amateur station. ASU does have a ground station. And they also provide the ability to schedule observations of any satellite, I think, not just amateur ones. They have a really nice dashboard interface, so you can see the dashboard for LightCube here that has all of the relevant information for the satellite, as well as places where you can download data, etc. And this ended up being really critical to us figuring out why our Cubesat stopped talking to us, because we only had 24 hours worth of data, and SatNogs was really, really critical in getting us that coverage. To show that again, I hope this is okay resolution. It's quite a saturated plot, but I went to the SatNogs API and I pulled down all of the known locations of SatNogs stations. Those are the black X's, and then the red squares are SatNogs stations that we were actually able to get and decode LightCube telemetry from. Had we been only operating with our own ground station, you would only see a red dot in Arizona, but as you can see, we got pretty good coverage from a lot of different locations. The actual demodulator was all done in a GNU Radio companion flow graph. I've seen a whole bunch of people put these up on their slides, and I can never read them, so I'll just talk you to the basic steps. This one assumes that you're using a file source, but there are also versions of this flow graph that work for a live hardware decode or a SatNogs audio file. This particular file source is assuming raw IQ, so you do have to do the narrowband FM receive yourself. SatNogs does that for you if you're using a SatNogs observation. The AFSK scheme then needs to be demodulated to soft symbols, converted to hard symbols, and then we have to sync on some sort of packet preamble. We use the amateur call sign in the LightCube packet header here. And then there's a bunch of data massaging just for the particularities of our modem. And then those packets are written out over a UDP sync to a Python packet parser, as well as written to a file for later use. So this was able to be used both by the LightCube team, and we put it up onto the SatNogs forums, and we had a couple interested amateur parties who were able to use this flow graph to get their own LightCube decodes. And now I will point out that this was heavily supported by the GR Satellites package. Daniel Estevez, who I think has been mentioned a bunch of times in this conference, has this lovely package that does that has some drag and drop demodulators. So this AFSK demodulator that you see in my flow graph is a drag and drop from that package. I think I use a couple other blocks of his, like the sync and create packed PDU. And this was especially critical. I did build this from scratch at first so I could learn how to do it. So I made my own AFSK demodulator, and having something to compare it to was really particularly useful for me. The published version uses the GR Satellites one because it does work slightly better than mine. A little bit of statistics. We got 531 packets from our Cubesat over that roughly 24 hours. About 80% of them were usable after basic checksum. And here's where I get to the kind of interesting part, is that when we went back and we looked at all of our received packets, almost all of them had a reported battery temperature from the Cubesat of at or below 0 degrees Celsius. 0 degrees Celsius is the minimum recommended operating temperature of the batteries used for LightCube, so that was not a very positive sign. Another view of that is I plotted the solar altitude at the Cubesat location versus the battery temperature, and you can see that it is very much correlated. So when there is good solar irradiance, the Cubesat warms up a little. When it's in the shade, it's very cold. We tracked this down to an issue where the battery heater was left in a pre-launch testing configuration, turned off, so the Cubesat was pretty much at the mercy of natural solar heating. And I will again say that had we not had all those great SatNogs observations, we probably would have had 3 points on this plot, which wouldn't have been super exciting. So a couple of conclusions. Lessons learned from LightCube will be used for future missions, both in the sense of like actual lessons learned of what went wrong, and in the sense of LightCube was a big team of many students who learned a lot building the project and will go on to work on future missions and use what they learned. We think that we're unlikely to hear from LightCube again just because there's been a pretty long lapse in communications now, but we are still looking out in case it ends up in an orbit that has a lot of time in the sun and it warms up and communications start again. And projects like SatNogs and GR Satellites are great and really useful for beginners. Consider contributing or using. I'm happy if anyone from those projects is here or online to kind of discuss issues that I ran into that might be useful for you. And if you want to learn a little more, I have a couple contacts here. You're obviously welcome to contact me. Christopher did the DTMF part of the comms, so he's also perfectly capable of answering any of your comms questions. And if you have more general questions about the Cubesat, Jaime or Professor Jacobs at ASU are both kind of higher in the LightCube hierarchy and can answer more broad questions. If I have any questions.
All right. Sam, are you say okay? Do we have a question? Okay, you do have a question. Sorry.
Yeah, sorry. So you talked about it potentially getting in a different orbit. Is it still? Are you tracking where it is? It hasn't burned up yet, or?
Yeah, I don't actually remember how long it's expected to stay in orbit, but it definitely still is, and I think we still have pretty good TLEs for it, so we're able to schedule SatNogs observations.
You like to get your TLEs?
Ooh, that's a good question. I don't remember where I got the ones that I used to make the plots in this presentation, and I also don't remember where SatNogs get theirs from, but SatNogs does have a TLE on the satellite dashboard page, so you can look at where that one came from if you're interested.
I see no more hands. I'm going to ask, other than this being really, really cool, like what's the point of having a satellite that goes blink? Is it is there a scientific additional value?
Not a scientific value. So I very briefly mentioned that it was educational on two fronts. So the point was to be able to have the public interact with the Cubesat. So it was very much educational. In fact, kind of the opposite of science. A lot of astronomers did not like it, but.
Well, I like it. Well, thank you very much. I guess everyone, you also liked it, so one more round of applause. And our next, did you have, no, our next speaker, Jean-Michel, is also not here, but he is also a long-time member of the GNU Radio community. Do you have the thing queued up, the video? Is that, okay, cool. So I'm going to quickly, oh, I've forgotten the title. It's a very long title, which it would take me a long time to say, but that is not the case for Jean-Michel. Yeah, long-time member of our community and always has very insightful, there we go. You can read it yourself. I'm just going to leave it at that.
Thank you for attending this presentation about time of flight measurement with subsampling period resolution using software-defined radio. The context of this investigation is radar, or more generally time of flight measurement using software-defined radio. And in this setup here, what you can see is two X310s connected to 4 cables linked on the roof of this building to antennas tuned to 143 megahertz, which is the frequency of the GRAV radar, the French space surveillance radar, whose emitter is located about 30 kilometers from our location. And in the context of distributed radar measurements, we're interested in having these 4 channels of both X310s connected or clocked, synchronized with these White Rabbit switches. White Rabbit is a PTPv2 protocol for synchronizing over computer network with synchronization, so frequency tuning of each switch. And so between these 2 White Rabbit switches, there's a few kilometers of optical fiber which improves the azimuth resolution of such a distributed radar system. And if we have a quick look at the GNU Radio flowchart that is running here, what we can see is the frequency offset introduced by a Doppler shift. GRAV radar is a continuous wave radar at 143 megahertz. So actually the frequency offset happens to be the speed of a target. These are live planes flying over our location, and here I emphasize the benefit of having a high stability oscillator. Here we are clocked on hydrogen maser for these 2 X310s, and this X310 has been tuned to be running on its internal quartz oscillator, and you see here the frequency offset between the quartz oscillator and the hydrogen maser. On the plot here, you've got the various frequency offset introduced by the various planes flying over our location. We are located over here, GRAV radar is somewhere over here, and all these planes have been flying overhead, each one of these turns being one of these angle on the chart leading to a shape different from the arctangent expected from a straight flight. So this is our context of application, and the question we're asking is whether we will be able to improve the range resolution under the assumption of a broadband radar signal beyond the sampling time interval. Indeed, under software-defined radio receiver condition, we assume we have a continuous stream at sampling frequency fs, so that the time interval between 2 measurements is ts, and the radar range equation tells you that the inverse of the bandwidth defines the resolution with which the time of flight can be measured, simply because we have a 2-way trip, so 1/2 of the inverse of the bandwidth multiplied by the speed of light c, 300 meters per microsecond, gives you the resolution with which you can identify a target range. Now, by using various processing techniques and under some assumption on the signal shape, can we improve the time of flight measurement beyond this sampling period ts? Of course, if we're asking the question, chances are that we're going to be able to answer positively. And what you're seeing here is a simulation, numerical simulation, where we generated a pseudo-random sequence, removed the mean value, and we spread the information with adjacent samples by using a convolution, so that the pseudo-random sequence, whose correlation should be a Dirac function, is spreading information on the 30 adjacent samples. And then we do a correlation between the reference signal and the time offset signal with index m, with m equal 1 to 6. So you here have the spreading of information at adjacent samples. We do the correlation, and so you might have always a correlation peak at the same location because of the spreading. But you see from the shape of a correlation peak, if we zoom into here, into this correlation peak, we see that the shape will be changing and will allow us to have much better accuracy on the time delay than just one sampling period. And actually what we can show is that the improvement on the time delay resolution is equal to the signal to noise ratio. So this is the basic of improving of a super resolution measurement by trying to fit the correlation peak. Now, spreading a spectrum, which defines the width of a correlation peak, can be done in many ways. We can send a short pulse, which is a pulse radar. We can sweep the frequency either as steps, a frequency step radar, or by sweeping continuously, the FMCW radar. What I like here is a noise radar, where a random sequence is generated, and this random sequence is actually recorded on a reference channel when a surveillance channel, a measurement channel, is looking at time delayed copies of this reference channel. And here we will try to improve the resolution beyond the sampling period by using correlation. Now, here is an example of a measurement we've been running for a few years now, where we are measuring DCF77 broadcast from Germany PTB, and we are recording the time of flight with respect to GPS. The signal from DCF77 is not only amplitude modulated as your watch is decoding if you're living in Europe, but is also phase modulated. And this phase modulated signal is spread over a bandwidth of about 700 Hertz, so that you might have something like a timing resolution of 1.5 milliseconds. What you actually see here is on this long-term measurement, we have much better than 1.5 millisecond. And if we zoom into one of these regions, you actually have the day and night ionosphere fluctuations with a line width which is about 10 microseconds. So the improvement over the 1.5 millisecond is 100-fold, which is about the signal-to-noise ratio of the received signal at a range of 400 kilometers, which is the distance between our location and DCF77. So this is the experimental setup that will allow us to try to answer the question. We have our software-defined radio, dual coherent input. That's a very important aspect. It has to be a dual input SDR. So we're investigating X310, B210, or as an example of a Lime microsystem 7002 front-end fitted software-defined radio, the XTRX from Fairwaves. These two inputs will be fed the pseudo-random sequence number that is generated by a field programmable gate array, an FPGA. And this FPGA will be clocked by the same time and frequency source than the X310, B210 software-defined radio, or XTRX. So this is our GNU Radio flowchart with one X310 or two X310s, both of which are feeding a file sync. So we end up having 4 files, and we clock them with the external sources to make sure that it's indeed the same signal that is clocking the FPGA that is indeed clocking the X310 over B210. Experimentally, this is what it looks like. So we've got our 2 software-defined radio, which are explicited now, and the 2 software-defined radio here are fed through a series of splitter, the 70 megahertz output from the FPGA, which is binary phase shift keying modulated, BPSK modulated with a pseudo-random sequence. And because the FPGA cannot be fed a sine wave, we have a fast comparator that converts the 10 megahertz sine wave into a square wave, feeding the clock of the FPGA. The distribution, the clock distribution, and the 1 PPS is either generated by an octoclock or by a small FPGA, which is itself generating the 10 megahertz and 1 PPS using the counter as programmed by Gwen. If you're interested, you have a portable implementation for all these types of FPGA using Amaranth language for describing such a pseudo-random sequence generator. Now, so the measurement we're doing is we are sampling at a rate of 5 megasample per second, so 200 nanosecond sampling period, many times the signals from both channels, and we fit the correlation peak to try to see how the time delay fluctuates. So if we do a single channel measurement and we repeat the measurement multiple times, we see that within each measurement the fluctuation is very small. It's in the few picosecond range, but from one measurement to the next one, the time delay fluctuates randomly within the sampling period. Remember, the sampling period is 200 nanoseconds, so here we see a random fluctuation in a few tens of nanoseconds from one run to the other. If you look closely, you will see two lines here, and that's because when we run the measurement, both channels are actually delayed the same amount. We're going to discuss this later, but from one measurement to the other, this random delay fluctuates. So on the B210, we can slightly see the two lines here. On the X310, the two lines overlap, and this is only 5 measurements. Later, we're going to repeat the measurement 1,000 times, but this is just to help you differentiate the various contributions on the experimental setup, again, where the FPGA output is bandpass filter around the output frequency, the carrier of the BPSK signal, and split between the two inputs. So the conclusion is we will not be able to use a single channel measurement, and just before switching to the next slide, the improvement on the B210 is due to the fact that the B210 has a very complex radio frequency front end which integrates amplifiers, the AD9361, and that allows us to use the full scale despite the 20 dB loss of the surface acoustic wave filter, whereas the X310 is fed directly the A to D converter inputs here. The full scale range of the X310 is about 6 dBm, and because of a 20 dB loss here, we are much below full scale range of the A to D converter, hence the lower performance of the X310. Later, we will add a few amplifiers before the splitter here to use the full scale range of the X310. So now if we look at differential measurement, where we compare one recording on one channel with respect to the other, this time the result is much better. Previously we had fluctuation in the tens of nanoseconds. Now if you look at the y-axis here, which is also graduating nanoseconds, this time the fluctuations, this is 20 picoseconds. So now you see that from top to bottom over these 5 measurements with 100 picosecond delay fluctuation, we have an offset of about 250 picoseconds from one channel with respect to the other, and the standard deviation is about 40 picoseconds. Now the B210 is fitted with this very complex radio frequency front end, and which might introduce some uncontrollable delays from one measurement to another. We don't exactly know how all these analog and digital front ends are behaving. So if we go to the much simpler X310, because this time we only have an A to D converter sampling at 200 megasample per second feeding the FPGA, no radio frequency front end, you see this time that the standard deviation is in the picosecond range as opposed to the few tens of picoseconds we had earlier. So if you look from the maximum to the minimum, we have about 7 picoseconds over these 5 measurements. And interestingly enough, in this experiment, we had the exact same length of cable between the splitter and the input of the X310. And for experimenting, we introduced one of these SMA right angle on one of the channel and not on the other. Now, if you look closely here, you see that we have a time delay initially of about 90 picoseconds, and when we introduce the right angle here, we decrease to about 15 picoseconds, which is over here. So we had a shift of time delay of about 75 picoseconds, whether the extension here is introduced or not. Now, if you consider that the speed of the electromagnetic wave in the coax cable is about 66% of the speed in free space, or 200 meters per microsecond, then the 75 picosecond delay lead to about 1.5 centimeter additional length on one length with respect to the other, and 1.48 centimeter is not ridiculous with respect to this computer-assisted design model of the SMA connector, where each length here is given as 7 millimeters, adding to 1.4 centimeter. If we generalize this measurement, you see here the experimental setup with the X310, the FPGA pseudo-random sequence generator, feeding the splitters and the amplifier, going to both inputs. Initially, both inputs are equilibrated with the same length, and we slowly add this 1 centimeter extension on one side of the measurement channel, and every time we add one of these extensions, we add a few tenths of picoseconds. And what you see here is the delay difference as we are adding more and more SMA extensions. The standard deviation is about a fraction of a picosecond. What you see here, 5 10 to the minus 13. And if we consider that the sampling period was 200 nanoseconds, now we have improved if we have here 5 10 to the minus 13 standard deviation, then it means that we have improved 400,000-fold the timing resolution of the system, and that is due to the excellent signal-to-noise ratio of a wired connection as opposed to a wireless communication from the FPGA to the inputs. And so it means that you can measure a few picoseconds by using such a narrow band, if you want, signal as 5 megahertz, thanks to the signal-to-noise ratio improvement. Here we had one night between the measurement, the first half of the measurement, the second half, and here we actually had 3 days, emphasizing the reproducibility and the stability of this experimental setup. Now that we're convinced that we can finally measure the time delay with much better than the sampling period between two channels of the X310, we might wonder whether it's actually needed to clock the X310 on the same reference as the FPGA. And what you see here is, because now we're running the X310 on its internal oscillator, you now have a drift of one oscillator with respect to the FPGA, because the frequency is different and the phase is the integral of the frequency, and yet the two channels are seeing the same drift, so that at the end, when we do a differential measurement, we subtract one curve with respect to the other, which was shifted for clarity, we end up having a flat line, and again we have a standard deviation of about a picosecond with some mean value, which is over here, and maximum minus minimum to minimum, which is about 2 picoseconds. So actually you don't need to reject the clock the drift by running the same oscillator. As we've seen earlier, when we're running this radar, what you might have seen here is that the frequency offset was due to the frequency difference between the quartz and the hydrogen maser, but still, if we're doing a differential measurement, we will cancel this common mode frequency offset, and we can finally measure the time delay between both channels. So this works nicely on a single B210 or a single X310. We can do a differential measurement of one channel with respect to the other, but can we multiply the receivers? The architecture that we're considering here is 2 X310 with 2 splitters, and actually all channels inputs are fed the same pseudo-random sequence. I'll show in the conclusion that the practical application would be to have each X310 with one channel measuring the signal under investigation, the other channel recording the PRN sequence for synchronization, but in this case we are feeding all channels of all X310s with the same pseudo-random sequence. Now what you're seeing here is, if we're doing a single channel analysis, as seen earlier, you will have a random distribution of the delays between something like 30 and 100 nanoseconds, and remember, this is the sampling period of 200 nanoseconds, so from one measurement to the other, the measurement will just randomly start at some point in between the sampling periods. If we do the differential measurement, here you see the overlap of all the 1000 measurements, so the thickness of a line tells you the reproducibility, and on this chart we took the mean value of each one of these 15-second measurements, and we plotted the time evolution. So each one of these measurements lasts 15 seconds, and for each 15 seconds we take an average, and we plot here one measurement after the other. So what you're seeing here is that on the short term, within each measurement, each X310, the first one with channel 1 minus 2, or the second one with channel 3 minus 4, exhibits a sub-picosecond standard deviation, and so do channel 1 to 3, which is one X310 with respect to the other X310. So on a short duration of about 15 seconds, the two X310s are behaving very similarly. However, from one measurement to the other, so along this axis here, we see that each X310 individually is exhibiting sub-picosecond standard deviation, but when we compare one X310 with the other, we have a much thicker line, which is this 1.6 picosecond, which is still much below the sampling period, but you do see that by comparing one X310 with respect to the other, rather than the two channels within an X310, we do degrade the performance. Now that we have looked at two X310, we might wonder what's going to happen if we try to synchronize on the one hand one X310 and on the other hand a B210 with the same layout, with all four channels being fed the same pseudo-random sequence. Now this time what you see is that within each SDR, if we compare one channel of the X310 with the other channel of the X310, or one channel of the B210 with respect to the other channel of the B210, well, we come back to the same conclusion as earlier, is that the B210 is degraded with respect to the X310 due to the uncontrolled delay of the complex AD9361 front end. We can see this over here. So your standard deviation of the X310 is 2 picosecond, where the B210 is a few picosecond standard deviation within each channel, within each measurement. However, when we repeat the measurement one after the other, what you see here is that this curve here is a zoom on this region when we compare B210 or X310 with each other, but the green curve is one channel of the B210 with respect to a channel of the X310. And in this case, you see that the fluctuations are basically random. We explain this by the fact that the clock mechanism of the B210 and X310 are completely different, and furthermore the communication scheme is also completely unrelated. One of them has an USB communication that will trigger the acquisition, when the other one is an Ethernet communication. Also, we don't know where the 1 PPS is sampled, and whether it's before and after the PLL, if it's sampling the 10 megahertz, but then the 10 megahertz is multiplied by a phase locked loop, then the time delay between the various channels of the two SDR will be completely different. So both messages and synchronization handling mechanism between being widely different, you see that it's impossible to synchronize a B210 and an X310 on what we've shown earlier, despite the fact that within the X310 or within the B210, both channels are nicely synchronized from one measurement to the other. Finally, all these investigations have focused on analog device front-end or no front-end at all for the X310. What about Lime microsystem? In this example, we're comparing the synchronization of an X310, which is used always as reference, with an XTRX from Fairwaves with its Lime microsystem LMS 7002 front-end. And what you see here is that we have a much lower performance of the XTRX LMS 7002. This time we have a few hundred picoseconds. So the layout from GNU Radio Companion is to have, again, the same clock distribution that we had earlier using the octo clock, the same signal feeding all inputs, the UHD, USRP of the X310 feeding two files, and the Osmocom source driving the XTRX feeding the other two files. And what you see is actually that not only are the measurements randomly distributed within the sampling period, but actually the XTRX exhibits a much lower performance, and this 20 nanosecond value here represents the fact that the measurement, the time delay between the two channels are just randomly initialized. Now, if we zoom and cancel the initial offset, saying that we run continuously the measurement and we can just remove the initial offset, well, still you see that the LMS 7002 is drifting over the 15 seconds. So we are again overlying all these measurements, all these successive measurements, and what you see now is that the XTRX is actually drifting over 15-second measurement, as opposed to the X310, which is extremely stable during each one of the measurements, as we've seen earlier. And of course, because the XTRX is drifting, if you're comparing an X310 with an XTRX, you get something that is drifting as well, and that will prevent fine timing analysis when you're using this Lime microsystem frontend. So as a conclusion to this whole discussion, we've been discussing how to distribute a fine time information by using a spread spectrum technique, recording on a reference channel of a software-defined radio receiver, and looking at the standard deviation of radio time delay of various radio frequency frontend. Our results are in compliance with publications from the Japanese group that developed YY for over-the-air high-resolution synchronization from NICT, and what you see here is a copy of one of the publications of this group, where they characterize the time delay between two channels of a software-defined radio receiver, and similar to ours, they can easily measure 10 picosecond delays with sub-picosecond standard deviation. Now, this all works very well with analog device and no front end. For the XTRX, we've seen that it's not so easy, and that actually asks for some performance question on the XTRX, because if you want to do some long duration correlation for example, extracting a weak signal from noise by long integration, you lower the, as would be done by averaging, you lower the noise and you accumulate coherently energy on the correlation peak. Well, due to the drift that we've seen, like the 200 picosecond over 15-second integration duration, if you were to work at 1.57 gigahertz, which is the GPS L1 carrier frequency, 200 picosecond is 110 angular phase rotation, which will lower your coherent energy accumulation capability. And even for direction of arrival, if you had some long integration duration, you would degrade your direction of arrival measurement capability. So as a conclusion to this whole presentation, this is the actual architecture that we are investigating, where multiple software-defined radio can be looking at different frequency bands. For example, in GNSS, L1, L5, and L2 are all in very different carrier ranges, well beyond the bandwidth of each software-defined radio receiver, but by frequency shifting using a local oscillator, the incoming signal, and sampling with multiple software-defined radio receiver with one channel connected to the radio frequency signal and the other channel connected to our pseudo-random spectrum spread information from the FPGA. We can synchronize all these software-defined radio receivers and realign the samples that, despite they were collected at very different frequency ranges. In case of radar, having multiple frequency bands increases the range resolution by increasing the bandwidth of recorded signal, assuming that the transmitter is located, all transmitters are located at the same location, as is often the case, for example, for digital video broadcast signals. So with that, I thank you for your attention and hope you will enjoy reproducing this experiment by yourself. Thank you.
Yeah, and I'd also like to thank Jean-Michel. So he is online. You can ask him questions in chat, and he was probably watching. I don't know. He's probably not watching the stream of his own video, but he's available for questions, and that was really cool. And I always like the rigorousness that his talks bring to these events. All right, I'm not gonna take your questions and forward them to him. Like I said, we can do that in chat. We now have lightning talks, and all of our lightning talk speakers will be familiar faces. So I don't need to introduce Derek. So but while Derek is setting up his laptop, I'll just mention that he will be talking about LiteX and GNU Radio. So LiteX, L-I-T-E-X, the FPGA development framework that well, Derek will talk about it.
Do you want to get the other two queued up, Paul and I?
Wiley, right? Yeah. So is Paul here? Okay, are you ready for your lightning talk? Are you ready for your lightning talk? Okay, cool. I think you're up next, and then Wiley will be after Paul. Oh, okay. Do you wanna go before? Do you wanna go straight after Derek, because I don't see Wiley right now, and then we'll have that. Or did he raise his hand? No. Wiley, are you here? And I'm not seeing you? Oh, sorry. Okay. Do you want to go first, or do you want to let Paul go first? Okay, so it'll be Derek, Paul, Wiley, and I think that's everything before the lunch break. Are you ready, Derek? So.
I believe so. Is my laptop showing up? Wonderful, great. Okay, this will be a lightning talk in the most genuine sense of these are slides that I have thrown together in a lightning fashion. This is a project that was inspired by a throwaway comment about 4 years ago at GRcon, and it's been the bane of my existence ever since, because this is a really cool idea that I wish we'd gotten a lot farther on. Obviously we're not at Berkeley SETI in 2021, so ignore all of this slide. I will be talking about LightX. This is a system-on-chip generator framework, which is open source. It's developed by Enjoy Digital, Florent in France, and it is written in Python and NMyGen, which is a Python-based hardware description language. It fully renders out to Verilog, so it is compatible with integration in many other tool chains, and it is also compatible with integrating VHDL, Verilog, and other languages within it. It is deployed out on a number of SDRs as its primary gateware. The HDL component of the FPGA is written in this, and so it is field-proven and fairly mature. LightX, this is a very quick enumeration. Mostly we'll post up the slides and links, and so you can follow that on, but it is fairly featureful and very easy to use as somebody such as myself who is not an FPGA developer by primary role. I can take some code, I can modify it, but that's really a stretch. So if I want to dig into something like an entire system on chip with PCIe and other components, this is really a helpful tool for me. So what did I want to do with this? I wanted to connect up a bunch of basically GNU Radio style blocks within an FPGA. Haha, isn't this a familiar concept? And so as a relative beginner, I wanted something that would basically plug and play this. So apologies to Florent. This image, I don't know if it's actually currently available on the internet, but I promise it has been in the past, so it's relatively public. There was a concept called Light Accelerator, or Light Compute, which builds upon LightX and strips out the RISC-V processor and a lot of the architecture that is there. If that's of interest, go check out the ability to run LightX processors and Linux on board FPGAs, that this tool just drops out the entire environment. But I want to be able to take samples in via PCIe, stream it through a whole bunch of blocks, and then back out the PCIe. So what does this look like in code? And my goal is just to motivate you to that. This is really cool. I have some pieces here that we can hack on tomorrow, and I can show you how this actually runs. This is the base of the system on chip, so it's a really quick declaration saying, I want to inherit all of your good work and do very little with it. Give me a PCIe interface, so the variant is just telling what hardware I'm using. I'll show you a picture of that in a moment. And give me a PCIe interface, please, with some configuration settings. And self.add PCIe, add this PCIe to the system on chip. Done. And then I have 2 blocks that I'm calling compute modules. Please instantiate those and connect them up into a pipeline. Please give me PCIe DMA straight into Compute Engine 1, then into 0, and then into 1, and then back out a DMA sync on the PCIe. I mean, look familiar and look approachable? Yes, please. So what does this compute engine actually look like? I am no DSP engineer on FPGAs, especially not on the about 3 weekends I've had to play with this. So for this, the pipeline stages are just adding 1 to each sample value that's going through. So within GNU Radio, we can do it's a constant add. But proof of concept, this streams really quite quickly, and I can get about 200 to 300 megasample per second through on this tiny little board that I'm using. So conscious that I am running out of time, the board that I'm using is this. It's a tiny little Bitcoin miner, which came available on eBay in mass supplies when these became completely obsolete. It's an Arctic 7 200T FPGA, so it doesn't require a paid license of Avato. The LightX toolchain will just do all of the FPGA build itself. It's tiny, and I have it in a little Thunderbolt enclosure. Kind of as a bit of motivation, my goal for tomorrow, if I have time to hack on things, is to integrate this tool, which generates compatible FIR filter code into this block. It should be copy and paste. We'll see how far it goes. But it's a really cool tool, and I had a student 2 years ago actually write GNU Radio blocks. So we have a PCIe source and sink that will send data to and from GNU Radio host streaming environment and DMA it out to the PCIe. So apologies for not really having a demo running, but catch me sometime and I can show you how this works. If this looks cool to you, I would love to have somebody else help out with this. I'm hoping to have a little bit more time, but that's about as far as I've gotten. There's a lot of documentation online with all of this, and I can send you a link to this compute test. Florent did the vast majority of the bulk lifting on this, and I'm really just pointing it out as something that I consider very cool. With that, I'll be around. Please ask me questions then, but Paul, I'd like to invite you up to present your work.
Thank you, Derek. Quick question while Paul is heading up, by anyone?
This is the entire FPGA module, and it just runs over Thunderbolt and USB, so you can load the FPGA over PCIe and lots of other fun features.
Hi everyone, I would like to tell you about a very fun project that we sort of accidentally almost ended up doing. Artemis 1, as you might know, is NASA resuming missions to the moon. Dwingelo is a very small village in the Netherlands where a bunch of radio amateurs and amateur astronomers are running a 25-meter radio telescope. Where's the clicker? You took the clicker. Oh no, here. And NASA, I think just 3 weeks before the original launch date, did a request for expression of interest. They were looking for parties that were interested in being a ground station. And that actually meant they wanted us to do one-way Doppler measurements to help with the orbit calculations, because the thing had a very complicated orbit, retrograde around the moon and then back to Earth. There was a lot of paperwork involved. For instance, you had to explain how you could guarantee that you were not going to accidentally transmit on S-band, which was very easy for us, because at that time we didn't have a transmitter for that band. And also what kind of frequency accuracy you guarantee and stuff like that, which I'll address in a future slide. Anyway, they were looking for collaborators on this project. That was one too quick. And in the end, they selected 18 ground stations. And as you can see in the circle, one of them was a non-profit, CAMRAS, which is a C.A. Muller radio astronomy station in Dwingelo, as a non-profit. And there's also a few people doing it with their personal equipment. There's some universities, there's some companies in there, but we were the only non-profit that was selected to help track this mission. I'm doing this talk on behalf of a lot of volunteers, and this is, I think, not even half of our volunteers, but just when we had a photo op. I think it does include most of the people, at least, that did help out with the Artemis mission. And you also see the telescope behind it, or at least the lower half of it. Above this, you have to imagine a 25-meter dish. Yeah, thank you. We had a pretty complicated software setup. There's something missing in the slide because we start with RF and then immediately, so there should be a B210 in there somewhere, but data comes out in Diffie format and we send it to all kinds of applications at the same time. First of all, we record it into SIGMF data, of course. We stream it into RTL TCP so that you can directly listen along on our websdr.camras.nl, where you can listen to all the various antennas that we have in the feed and around for meteor reflections. We were streaming it to, what's that again? To GQX, so that we could actually see it in ourselves while we were in the telescope. And then we ran it through a block FFT max. It simply takes an FFT over 1 second and tells you what frequency had the highest energy, and that is basically the data that we would return to NASA. Of your tracking tone, we found it at this moment in time at this frequency. However, most of the mission, it would not be sending this tracking tone, it was actually doing QPSK signal. But the nice thing is, if you have BPSK signal where the phase flips back and forth by 180 degrees, if you square that signal, you end up with removing all the modulation and you end up with a tone. And with the QPSK signal, you simply need to square it twice. So we did it to the fourth power, so you have a nice tracking tone. The other advantage is that in 1 second, you suddenly get a quarter of a hertz resolution to return, which is even better. We also sent the short snippets to SIGMF, and we also had a coupling so that we could look at it live in GNU Radio and make even more processing if needed. Well, you can't have a slide about space stuff without mentioning Daniel Esteves, and just after we got started, he kindly informed us that, hey, I'm doing the same at the ATA, and with a single 6-meter dish, I'm getting a much better signal to noise than you do. So that was just a little bit of head scratching, and then we had to get in the elevator, as you can see in the image. That means going up, going to the feet, and then we had to swap the polarization, and then things went a lot better after that. And that is after at least checking that we had the correct polarization at least 3 times beforehand. So what do we actually see? What you see here is frequency, or actually the residual between the prediction from the JPL Horizons website for the Doppler shift to our location versus what we actually measured. And then most of the time it's a very constant tone, very slowly changing until there is something like an orbital burn, and then you see all kinds of squiggles. And what's even more interesting, when you've got the audio turned up, you can actually hear it. You can hear the frequency shift around as the rocket engines light. So this station was transmitting an S-band. We just received it on a B210. And in order to give meaningful data back to NASA, we had a hydrogen maser as the reference, not our own hydrogen maser. We actually were using the one from the Westerbork telescope, but using our White Rabbit link to our telescope so that we had a traceable frequency reference. And in my earlier talk, and you'll have to see it online unless you can go back in time, I actually explained a lot about that hydrogen maser and White Rabbit link. So this is another burn. I think this was the burn where it left lunar orbit and started its return to Earth. And you can see before the burn, the expectations match the graph very well, and after the burn as well. The burn itself sort of matches, and in between there's a little bit of squiggles where possibly the data are more or less calculated for the JPL ground station and not for us. But yeah, we could track these burns, and we sent all that data to NASA, and we haven't really heard much back, I have to admit. And this is how it looked like inside the telescope. We had an extra screen, and you just see in GQRS, and just at the bottom you can see an actual frequency jump. And at the same time, in a window there, we were just streaming the live webcam from the spacecraft, and you could occasionally see it turn around, and you could see the tone change, and then it would burn, for instance. One of the more interesting results we had is, and this is not in frequency, but is in amplitude. Just as the spacecraft disappears behind the moon, eventually you get a direct signal and reflected off the moon to you. And the two interfere, and that can tell you interesting things about the composition of the lunar surface, or maybe even for some, well, not for the moon, but for other planets, it would tell you about the atmosphere. So we had some very good quality data on those occultations. And I want to end with telling you that you also can be involved in this. All our data is open at data.cameras.nl. You can see all the data from our Artemis mission, but also pulsar data, hydrogen data, all the other cool stuff that we get up to. So if you want to give a try decoding the data, or just tracking it a year after launch, be our guest. The data is available for everyone. Thank you.
All right, thank you, Paul. We have Wiley up. I don't know if other people have the same feeling. When I listen to these talks, I always feel a bit silly about how I spend my free time, because I'm not tracking spacecraft. All right, it's right there. You just push really hard, and those are your slides, right? Possible GNU Radio. Okay, cool. There you go.
So my name is Wiley Standage-Beyer. I'm a PhD student here at Arizona State University. Let that inform the rest of this talk. I'm an academic, not industry. And sorry, I'll make this quick, or if you leave, no hard feelings. I know, I'm competing against lunch. So how we currently implement GNU Radio block in Python requires a lot of boilerplate. You got to inform it what the inputs and the outputs are. You have a constructor, a work function, and yet most of the time, really, we just have some function that we're just calling on a NumPy array or two, and we want a NumPy array back. So one way we could improve this is we could write a decorator that implements all the constructor and work function calls, and we just, and the decorator would inspect the I/O signature of the function, and then have it, excuse me, have it infer what's a vector and what's a parameter that's to be handled by the constructor. Another thing we could do, we could add better support for custom data types. So I want to shove matrices and other weird stuff through GNU Radio as streams. I might be the only one that wants to do that. I don't know. So, you know, a pure Python thing may make that helpful. The other thing is hiding some of the busy work involved in using PMTs. I really like tag streams for adding metadata about, let's say, bursts or some other statistical event. There's probably a way by subclassing NumPy arrays to do that really elegantly. I don't have it fully thought out. This is a proposal. So the other thing is how we connect blocks. On the left is how it currently works. One way we could improve it a little is, let's say we were connecting multiple ports of a block. Instead of calling the connect function multiple times, we could introduce a slice operator in there. That shouldn't break anything because nothing else uses a slice operator on blocks. So this would be a little bit of Python indirection. And then with the same theme, we could introduce an addition operator. And then that could become another means of connecting blocks. So we could reduce 3 lines of code into 1 line of code from the left to the right, bottom right there. So, and then the other thing is I use a lot of Jupyter Notebook. I'm probably not the only one in the room, but I don't think there's a lot. But better, and this is not a GNU Radio thing, this is adding support to Jupyter Notebooks, probably via some kind of extension for GNU Radio. So we could hypothetically have it spin up a worker and then spin that out, and then we can manage it from within Jupyter Notebooks and have it non-blocking, even though we're calling the run method there. And then, hey, while we're doing it, we've got all the information there. Why not render it to the canvas so you can see it? I yield my time to lunch.
All right, thank you, Wiley. That's it for now. For lunch break, and then we start again at the usual time. Let me check. 1 o'clock, yeah. All right, see you later. Bye-bye. Ah, there you are. Perfect. All right. So we're about to start the afternoon session. It's 1 o'clock now. Actually, you in the blue shirt, can you close the door, please? And the other one's already closed. Thank you very much. We will continue our talk session now. It is the last half day of talks. Tomorrow there will be, more interactive events, but no more talks. Well, or at least none that we have planned. Before we start, quick announcement. So we started talking about 4.0 this morning. There was the panel, and we also had some talks yesterday, I think, on the actual details. There will be sort of a more informal chat in Copper at 1:30 for those who are interested in getting more involved in the details. But other than that, I'm just gonna pass it off to our next speaker, please.
So, hi, I'm Murat Sever. I'm currently a PhD student and a part-time lecturer at Tobet University, located in Ankara, Turkey. At our university, we made a transition from hardware-based communication system laboratory work to STR, and we have extensively using GNU Radio. Today, I'm going to share our experience with you. So I'm going to talk a little bit about the motivation for starting such a change, and then give you information about the curriculum that we have prepared. We have developed an undergraduate level laboratory coursework to teach communication systems to undergraduate students. So we also prototype a standalone kit that we can use in education for educational purpose, and developed a graphical user interface, a simple one. And lastly, I'm going to conclude with our future plans. So what are the problems in teaching communication systems? They are complex in nature, and they include many subsystems. And they involve theory, that's theoretical and hard to understand. Most of the time, laboratory work consists of simulations or some experimentation with hardware-based solutions, which are both expensive and difficult to set up. So the solution we are looking for should have an open architecture. It should be modular and extensible, should include real-world signals like narrowband or wideband FM or ADSP signals, or a signal from a remote key. And should be software-based, supporting professional development of students as well. And it also should provide us remote work opportunity. So simply, we ended up with a simple solution, a low-cost STR, which is RTL STR, that has only receive capable. And everything is installed on student's laptop. And we also developed a curriculum. All modular things are based on Jupyter notebooks. Consists of, it has many modules. And we begin with a DSP module, because there are students new to the DSP world. And STR module gives introduction to RTL STR. And Python or MATLAB module gives programming with Jupyter notebooks and other libraries. And all other communication system modules consist of we use Python, or they have records and walkthrough examples, and students take records and validate their algorithms to run on their own recorded signals. Students also apply their algorithms to the records themselves. In classes, I also transmit if there is no chance of low opportunity to be found over the air signal. So students catch it and record it and use the signal as a signal source. And we use GNU Radio for both signal analysis in real time and offline. And I'd also like to mention that I use GitHub up a classroom application. It's a free application for academic use. So it's easy to manage assignments with it. So, and we can automatically grade the assignments. It also allows you to watch the progress of the students and give necessary comments to them or collaborate. It provides a collaborative environment. So our main aim is to engage students more into communication systems through real-world signals. We also help them on their professional development and like building and improving their programming skills. The course is unique in some points. It has a mixed content like GNU Radio, general purpose applications and programming. And programming language can be Python or MATLAB. They are both supported, and it's remote ready. And this is a 10-week program in total. And in the first half, we go over installation of tools on students' laptop, introducing them to environments, to like Markdown language, Markdown, GitHub, and Jupyter Lab. We also go into the USB with GNU Radio, prepare them to our real topic. In the second half, we go over analog modulation examples, both from IQ records and over-the-air signals. We also see examples of digital communications. We have digital communication example, end-to-end example with BPSK and ADSB signals. I taught the newly modified SRBase course, laboratory course, 2 times so far. I received good feedback, and according to surveys, the students tell they grow interest in communication systems and they learn tools that are helpful in their future career. And this is the most standing out part maybe. I asked the students about their favorite module, and according to the polls, 2 GNU Radio modules became the most liked ones. At the first, I was surprised, but when I got the result for the second time, I taught at Fall 22, and the same result again. So GNU Radio is the winner. We will see that what will be the result for Fall 23 in a short time. And we were also investigating a low-cost embedded standalone system that we can use in other projects other than telecommunication projects. So like projects like computer vision, robotics, or other AI applications. And we decided to design the kit with NVIDIA Jetson Nano single board computer because it gives us heterogeneous compute platform to run broad range of applications. The prototype also includes a touchscreen display and a sound card, and it's a prototype, but it can become a portable one. We are utilizing Nano STR distribution from STR Technologies for Jetson Nano. It includes most of the popular software. So the student this time is eliminated from the installation process, and it can be used directly, instantly. So we later developed a simple GUI that easily launches the installed software with just one click, make it easier to use for ones with little experience, with little knowledge on devices or the applications. The left image shows the main window, and when you click one of the buttons, then GQRX or ADSB application, general purpose applications are shown, launched, and this way the user can easily watch common signals like narrowband FM or ISM band or ADSB signals with just one click, and they can start IQ record too. And we have two big supporters, and I would like to thank them. NVIDIA has granted us JSON Nanos through their academic hardware grants program, and we are also one of the grantees of ARDC. They support us to develop SDR-based education materials to help us improve our course content through their education support program. And this project is a work in progress. We will add more modules covering advanced concepts and maybe graduate study, materials for graduate study. And we also would like to use GPUs for accelerated computing and maybe add deep learning applications as to introduce students to this field. And thank you very much. I would like to also thank Dr. Michael Lustig from Berkeley and John Pauly from Stanford and Dr. Mark Leachman for their help providing us the course design, and I used their course materials and to design the course structure. So thank you for your attention. I really enjoyed my very first GR conference here. I'm happy to be here and hope to see you again. Thank you.
Thank you very much. Do we have any questions? We have some time.
So this morning there was a talk expressing interest in integrating GNU Radio and Jupyter Notebook. You mentioned that in your slides. Have you been doing that? Have you worked on that?
Yeah, actually, Jupyter Notebooks for GNU Radio integration, actually, they are separate. Most of the time, we are using Jupyter Notebook for programming, MATLAB or Python coding. Yeah.
Do we have any more questions? I have one question. So, when is the first time you did this class?
It was in summer 21, I think.
21, okay. So you mentioned like some testimonials from your students that were very happy. Have you had students go, like go for work after and then like say, okay, I really took some skills from this class that immediately helped me, I don't know, in my industry job or something like that?
Yeah, students mostly from third grade, and they can find internship easily, and they found the class helpful for their internship, and when they work in a in telecom job, which is not very much in Turkey actually, yeah. They the course helped them. Yeah.
Okay, very, very cool. This reminds me, last year we had a keynote, I think it was last year, by Dr. Laneman from Notre Dame, who talked about various software stacks and their various, curricula. And this is just a reminder that you can watch all of these talks later online. That particular keynote was an excellent keynote, and it talked about these things. Well, thank you very much. This was very interesting. Another round of applause, please. And I don't have the schedule up. Just the next. There we go. Perfect. We'll be hearing about moonbounds now, right? Looking forward to that. Yeah, Dennis, please take it away.
Okay. I'm Dennis Rosenauer. My day job's I'm technical director of R&D at FormFactor. Oh, I'm sorry. I'm usually used to talking to other people, and I can see this here. Okay, so what we're going to do is I'm going to talk about how to do EME, Earth-Moon, Earth communication. So we're going to reflect a signal off the moon, and we're going to do it with an SDR. But first, we got to do a little bit of training. We're going to try and learn a little bit about the analog part. The part that I'm going to talk about is between the antenna and the A to D converter. We're going to even include some of the A to D and D to A converter. We've got lots of wonderful software work going on here, but we need to focus on that RF pit a little bit. So first thing we're going to have to do is get a few references and a few definitions in. So the first thing we've got to realize is that we're talking in an analog world, and it's a power that we're dealing with. And we can represent that as a voltage across a resistance, or we just represent it as a power itself. So what happens is the powers can be very small in communications. You're receiving something, you're a radio astronomer, you've got a signal that ultimately maybe displaces a little bit of charge on a gate of a FET, or you've got a transmitter, it's a huge transmitter, you've got your microwave oven, it's cooking your lunch for you. So we have to deal with all those signals. And in EME, we're going to transmit with a large signal. We lose the audio? Okay. So just a few points of reference. We know that we can represent it as a voltage. We can represent it in dB. dB is a ratio measurement, and dBm is an absolute measurement because we have referred to 1 milliwatt. So we're going to be using these terms a lot. So let's take a look at amplifier properties. That's going to take into consideration a lot of active devices. We're going to start with an amplifier. And it makes things bigger in the case of amplifier, but it introduces distortion and noise. So it's not an ideal amplifier. It does introduce those. So let's see if we can quantify that, because that's going to limit our performance of our RF and our transmit output power system. So let's take a look at noise. So I'm going to go through here kind of quick. There's got some math in it. But what happens is we want to try and model this noise because we're going to do some calculations on it. So what we're going to do is we're going to model the world as a noiseless amplifier, and we're going to inject some amount of noise in it. And what we're going to do is we're going to bundle up all the noise that we have in the back end and put it into this synthetic source at the beginning, quantify it, then we can compute the signal-noise ratio coming in because we know how much signal we've got, we know how much noise, we get SNR, and now we can start doing some metric calculations of what our performance is going to be like. So the first thing we're going to do is look, what's their equivalent noise power? And with a little bit of physics, we realize that the noise power is actually equal to KTB, Boltzmann's constant times temperature times the bandwidth. So wider the band, the more noise, the higher temperature, the more noise. So that's the things we're going to work against. So how do we work this out? Well, the first thing we need to know is what the signal and noise ratio is. What's a degradation? What's the signal noise ratio out versus the signal noise ratio in? And that really is the definition of the noise factor. It's a number. It is greater than 1. If it's 1, there is no noise contribution. So the signal and noise is exactly the same on both sides. But the amplifier contributes noise, so the value is always got to be greater than 1. So what happens if we're going to have a lossy device? Let's say we've got some coax that got some loss or an attenuator or something. So let's start with the simplest thing. If we do some math, you can do these on your own. I'm not going to dig through all the details, but we'll find an interesting thing. The attenuation is exactly equal to the noise factor. And the other thing we'd represent sometimes is a thing called noise figure, which is the noise represented in dB, is a dB ratio. So it's 10 log that noise factor. So they're going to be used kind of interchangeably. And if you look through the industry textbooks on noise figure of LNAs or transistors, it'll often be in dB, but when you can do calculation, you have to convert it to noise factor many times. So this is one of the things you have to look out for. But if we're looking at a lossy device, mixers will fall into that, the noise figure is equal to the loss of the device in question in dB, or you can work it in noise factor, either ways. So the other thing that we end up doing is we're going to see what happens with an amplifier that has a known noise figure. You can get that from the data sheets, how much noise actually comes in, because we need to know that to compute the signal-noise ratio of the system. So we do another little bit of math, and you can follow through it. But we find out that the equivalent noise power is equal to KTB times the noise factor minus 1. So if the noise factor is 1, then the equivalent noise power is 0. So that extra noise power is actually 0. If the noise factor is 2, which would be a 3 dB noise figure, that means we're getting twice as much signal noise as equal amount of noise power going in as we get noise being generated by the device. So it degrades your signal and noise ratio. So what happens when we cascade devices together? We're going to have to put several amplifiers together because we don't have enough gain in one. What happens with the signal and noise ratio? So you look at this a little bit. There's a little bit of math to it, but what happens is every time you go through an amplification stage, you add a little bit of noise, then you amplify that noise with the next stage. So you have the signal coming through the first stage, it's got a little bit of noise, and then you're going to amplify it, so that noise, because remember we put it into the input, now is amplified by the same amount as the first stage, then it goes in the second stage and it adds its noise to it, and then that stage adds its gain to the signal plus the noise. And what you'll notice here, if you look at the graph carefully, that the signal-noise ratio at the output is less than the signal-noise ratio of the input. But there's another little sneaky part that shows up in the equation here. I think it's on the next slide. It says, if we do a little bit more math, we'll see that the noise factor of the total is dominated by the very first stage, and the second stage is attenuated by its gain. So let's take a look at that equation at the bottom. It says noise factor total, F1, that's the noise factor of the first stage, plus the noise factor of the second stage, minus 1, we're removing that input, divided by the gain of the first stage. So that means that your total signal-noise ratio degradation by the noise is going to be dominated by the first stage, and as much gain as you can get up front there is going to reduce the effects of the noise on the second and third and subsequent stages. You can cascade this equation together and do it from multiple stages. So you work at the back, from the back going to the forward to the front, and you can actually work out what the total aggregate noise figure of your system is. So the other thing we're going to look at is intermodulation. Now we talked about the weak signals, which occurs at near the noise floor. Now what happens when we make the signal really big? We've all seen intermodulation. We start turning up a signal, all this garbage starts showing up. So let's see how we address that. So let's see what happens in an amplifier. So you look at the amplifier, that red curve is the transfer function of it. If we have a small signal that goes, it deviates up and down that transfer function a little bit. So we have, say, for example, a 1 volt peak-to-peak signal. We compute the gain. It's a gain of 14. Do a little math. 20 log takes 10. Remember those first equations? Its voltage is 20 log. It's 23 dB. So let's make it a little bigger. Let's make that signal 2 volts peak-to-peak going in. Same amplifier. Output's now 10 volts peak, 2 times 10 volts peak-to-peak. We do the math. We get 20 dB. So all of a sudden the gain's dropped off. And what's been happening? What's going on? Well, what happens is you're driving the amplifier, and the amplifier can't go any further. It's up against the rails. The transistor saturates, or it goes to cutoff. It can't turn off anymore, and it can't turn on anymore, so the signal can't get any bigger. So that's what's starting to happen, and when you do that, it starts to degrade the quality of the output signal. Okay? That's what's going on. It's clipping the top and the bottom off. If you look at it, this is a little better graphic of it. You can see the green. That's the signal that it can amplify. And the red part is just not going to show up on the output. So you have this clipped waveform that's going to come out of it. Okay. So let's see if we can do a little bit of work with it. So if we describe that transfer function as a polynomial, remember you can do a Volterra series and things like that. And we say, well, what if we let all the linear terms prevail, like just A1, then we have a linear amplifier that's good from 0 power to the power of an exploding sun. So that's not going to work too well. So what happens if we have some higher order terms? So we put the higher order terms into it, and we use the second and third order terms most often. You can go to higher order terms if you want, but usually second and third order terms are what are used. And if we replace the signal with a sine wave or cosine wave, we can compute a couple of interesting things. The first thing we discover is that as the curve starts to heel over, so you have that cubic curve, we'll find that the gain actually limits. So when the ratio of that A3 coefficient relative to the A1 coefficient, when that ratio starts to get to a certain point, we can actually compute what the gain of the device is and when it compresses. So we'll actually find a point when the signal actually compresses. So what you'll see is that the amplifier can't go any further. So if we know something about that polynomial, indirectly is how we'll end up doing it, we can actually compute some of the performance of the amplifier without getting down to the transistor level, which makes life a lot easier when you're doing the system. Okay, so theory of two tones. We're going to put two signals into it, two sine waves, do a bunch of math, and we're going to find something really interesting. There's a couple of terms. There's one term there, it's in the sort of the middle, that's got a little bit of highlight, and it says we've got a signal that's twice, it's omega 2 minus 2 omega 1. That means that there's a mixing going on. The signal at frequency omega 1, there's going to be another signal being created that's omega 1 minus 2 omega 1, and another one's going to be created omega 1 minus 2 omega 2. So what does that look like in a spectrum? So if you look at it, you'll see we put two signals in here. We've got F1 and F2, and here they're megahertz apart. And we're generating, as we're pushing this amplifier up into saturation, we're generating this other signal that's going to be at 2F1 minus F2 and 2F2 minus F1. So I got 835 and 836 going in this example, and ended up generating 834 and 837. Where they're coming from? They're coming from that distortion as we're starting to encroach into that nonlinear domain, and now if you do the Fourier operations, you'll realize that we're going to be actually creating another signal. Power is conserved. You're going to lose power. Your main signals are going to compress, and you're going to generate these other signals on the outside. There's some other terms that come, some second order terms that show up, because there was that second order term in the previous slide. If you will take a look at some of those, you'll find that there's F2 minus F1 at the bottom end, and 2F1 and 2F2, so that's how your frequency multipliers work. Okay. All right, so let's take a look at that again. time domain on the left, you can see it's kind of two tones. You see that there's two tones in the frequency domain on the right. As you start to bring them up, you'll see that those other tones come up if you look at the spectral spot on the right, and that the signal level actually starts to compress. It clips. That we were talking about earlier, that the level actually can't go any higher, and it starts to clip off. Okay? So what happens here? Well, if we do something interesting and we convert this to a log plot, and I'm not going to, again, I'm going to be very short on the math. You can look at it at your own good time. We can plot some interesting lines. We notice that second order terms tend to go as at twice the slope of the fundamental term. So if you've got a gain, it's got a gain of 1. It's got a slope of 1, because P out is proportional to P in, or indeed P out equals P in plus some gain. The second order terms go up at a slope twice that. So for a 1 dB change on the input, they go up 2. And there's third order terms for every 1 dB in change, it goes up 3. So let's take a look at those. So here's a bit of a graph representation of it. So you can see the slope, or the area slope of 1, that's your fundamental signal. That's the one you want to amplify. There's another set of curves, those spurious that came up, those 2f1 minus f2 and 2f2 minus f1, they come up, and they'll come up with a slope of 3. And if you look at that very carefully, there's a point where the two lines intersect. One's a slope of 1, one's a slope of 3, and they end up hitting some point up on the graph. It's a synthetic point. You can't really get there because you can't amplify that high. But if you do that, you end up with a thing that's called third order intercept. So if you read the specifications of power amplifiers, they'll say third order intercept, or OIP3, which is the output third order intercept. And if you know that point, and you know the slope of the line, which you do because of the math, then you can compute at any power point that you like, well, how big those signals are. What's the signal level of those unwanted signals relative to the signal that you actually want to capture. So you can actually see that. So I'm going to transmit a signal, and if I push the amplifier too hard, I'm going to start generating these intermod products. And when I do that, I want to know how much room I've got. What's the signal-noise ratio on that? And if you look at something else, there's a noise floor on the bottom there. And if I look at that point where the intermod intersects that noise floor, that's the biggest signal I can actually carry in that analog amplifier. It's like running the maximum number of bits in your A to D converter. That's as big as a signal as that amplifier can do. Because in the bottom end, you're seeing the noise, and the top end, you're seeing the intermod. So you go any higher in signal, you get an intermod product. So as a consequence of that, you end up realizing that that's the maximum range. They call that the spur-free dynamic range. That's the same thing you see on A to D converters. It's also in the analog world as well, and that's those intermod spurs coming up. Okay? So you can do a cascaded analysis. You can cascade it. What you usually find is that the amplifier with the lowest IP3 relative to the signal level is going to dominate the system. So you can see this intuitively. If you have an amplifier that saturates early on in your power amplifier stage, let's say running at the 100 milliwatt level, but you want to go to 10 watts, and you've got a couple of stages to get there, but the 10 watt amplifier doesn't saturate, then that driver stage way down, that inexpensive driver, is going to saturate and dominate your performance. What you really want to do in design is dominate your intermod with the highest power stage, because it's the most expensive one to do it with. So the lower power stages, they're cheap or cheaper, and you want to dominate your IP3 on that. So that's how you kind of cascade it. Now there's two ways that those sum together. One is coherent, the other one's incoherent. In most cases, you do the analysis coherent, which is the worst case. That assumes that the vectors all add up like this. They're not some random vector. So you have one that's a square term, which gives you a lower value. So you want to take the worst case, because we're kind of doing system engineering. If you know something about your properties, you can sometimes do this as a non-coherent case. If you really want to know the answer, you've got to do a circuit level simulation, and you can actually compute it with much more accuracy. So here's another little sort of review of it. Here's IP3. You see that point on the curve? The slope is 1. The other slope is 3. Remember we talked about the second order terms? Well, you can have a second order intercept. And that's an important thing when you're dealing with zero IF receivers. So a lot of our SDRs that we have a zero IF. They convert down to some baseband. And what happens there is, remember we had F2 minus F1, and they come down at low frequency? Well, some of those will leak through the system, and they'll show up as a signal down in your baseband, and you wonder where that's coming from. That's F1 minus F2, and you're overloading your receiver front end, and it's getting through the system. So that will happen sometimes, and you have to watch it. And if you look at the specs on things like the 9361, there's an IP2 spec as well. So they've actually characterized that. So another thing to keep in mind. All right, so let's talk a little bit about A to D converters. The A to D converter is basically a high-speed voltmeter. All it does is it measures voltages as fast as you can get it to do that, for whatever the purposes it is. And it also generates some noise. The noise is going to be due to some signal across an internal or external resistor. So I'm going to have a signal I'm going to impose across that resistance. That's the power that the A to D converter is going to read. Remember, it's a voltmeter. To know the power, I have to know what voltage is across some form of resistance. That's what I have to compute. And I can compute a noise figure of this thing, or a noise factor of the A to D converter. So let's put that in, and we also have a band limiting. So we're going to start with the Nyquist bandwidth filter. So we're going to go sampling rate on 2. You can do math for different schemes, but that's where we'll start. So when we do a little math and put it all together, we can start actually computing this signal-noise ratio. So we can take a look at it this way. The full-scale signal that we can get, the maximum peak-to-peak value, is basically the smallest signal I can get in the A to D converter, least significant bit, and the fully saturated value of the A to D converter. That's the biggest signal I can get. I know the noise signal coming, that's KTB, B being the bandwidth, because I know how wide my band is. I know what the signal and noise ratio of the A to D converter is. If they don't publish it, then you can look at 6 dB per bit. It's usually 6.02 dB plus, was it 1.7 dB or something like that? That's a good rule of thumb. But usually it's a little worse than that because there's various quantization noises that show up, and you'll find that in the published data sheet. So now we can calculate it. So I did it here for AD9446, and it will go to 3.2 volts peak to peak. I'm using it's a differential input. Its published SNR is 82 dB, and the bandwidth is 40 megahertz, an 80 megasample A to D converter. We do the math, and we find out that the noise figure of this thing is 33.9 dB. So here's our pretty good A to D converter, and has an absolutely horrible signal. It has an absolutely horrible noise figure. That's why you have to put some gain ahead of your A to D converter. If you want to copy a low noise signal, you've got to put some gain ahead of it. But there's something you've got to watch. I can put the LNA in front. I can make the noise figure better. So we put a gain of 20 dB, or a voltage gain of 10, in front of that same A to D converter, do the math, and now that 33 dB noise figure is down to 14.9 dB. Remember that equation we derived earlier with the noise figure? We used it here. So now we can do this, but now we're at 0.32 volt peak to peak. That's the maximum signal. Okay. All right, AGC. So how do you keep this thing from going off the rails? Well, you build an AGC system in it. So what you have to do is actually control the gain stages ahead of the A to D converter to keep it between the guardrails. You want to be above the noise floor, so you got good signal fidelity, but you got to keep it below clipping so you don't end up generating garbage. So you build an AGC. How do you do that? Usually you take a little sample of the A to D converter, you compute the mean power out of it, mean squared power out of it, I squared plus Q squared, build an IIR filter of some description, little state machine, you control the gain. It can be digital, it can be analog. And sometimes there's a state machine that you control because you want to have a fast attack, slow decay. It's dependent upon the project that you're doing. Okay, let's look at D to A converters briefly. D to A converters also specify a spur-free dynamic range. So you have this maximum signal and there's some spurs. If you can filter the D to A converter, you can sometimes filter out the spurs that you're not using. So then you can actually have an effective higher spur-free dynamic range. And some of those spurs aren't generated by the A to D converter, particularly if you've got a D to A converter. Sometimes you have a D to A converter and it's feeding some up converter scheme, or it's an IQ modulator. You'll have carrier leak through or unwanted sideband leak through, which will be effectively the same thing as spurs. Well, if you drop the digital level coming in, the signal level will drop, but those LO leakage spurs will not go down. So what you really want to make sure is you drive the D to A converter at the maximum range. Otherwise, you're going to be degrading that spur-free dynamic range because those LO leakage spurs aren't going to get any lower. Now, some of them you can balance out to drop it down, but once you've got that established, you really want to have the maximum dynamic range available so you keep that spur level down because you're going to have transmitting those in many cases. Okay, let's see. So how do we do this with EME? So shoot for the moon, you might get there. I think that's a good shot of it. So what we're going to do is we're going to build a little EME receiver, which is we're going to try and transmit to the moon with a transmitter. We're going to get a reflection off the moon, and we're going to receive it. So let's figure out what we need to do that. So what I did is put together a system, use a blade RF. I got a power amplifier, I've got an LNA, I've got an antenna, and for frequency control, to make sure everybody's on the same frequency, use a GPS receiver that gives us a reference. So we're going to use GPS locked reference like we use in many cases. This case, I'm 960K samples per second IQ coming out of the blade RF. So what do we do to figure out what kind of signal loss we're going to? So the first thing we can do is we can get the radar equation. We can talk to the radar guys and say, hey, what do you know about the moon? And talk to the astronomers a little bit, and what do you know about space? And they give us a few coefficients. So we put those in, compute the loss. Lunar coefficient, reflection coefficient 0.065 or 6.5% of the energy comes back. We know the radius of the moon, the wavelength. We're going to do this on 1296 megahertz. And we know the distance nominally to the moon. So we compute the mean path loss, and we realize it's 271 dB. So it's going to be a small signal. So let's see what we're going to do. We're going to try and listen to a station that's in another location. He's going to transmit with 900 watts. He's got a 1.8 meter antenna, which gives us 26 dB a gain. We can calculate that from antennas. I'm going to listen to him with a little bigger antenna. I got a 2.4 meter antenna, and it's got 28 dB a gain. So let's do a little quick spreadsheet calculation, see what we're going to have coming back. He's going to transmit at plus 59.5 dBm, which is 900 watts. His antenna gain is going to increase that, so he's got an effective EIRP. He's going to narrow that power and put it in one focused beam. So he's going to be at plus 85, or 358,000 watts EIRP going up. Don't stand in front of the antenna. The path loss is 271 dB. I've got 28 dB gain. We do the math, and I'm minus 157 dBm, which actually is 172 times 10 to the minus 21 watts. Not very big. It will not warm up your coffee cup. So what can I do to estimate that signal noise ratio? That's what we wanted. Remember that signal noise ratio that we wanted? So let's go do a little bit of math. We know the noise of the system. We know that we've got KTB noise. We're going to assume 290K, and we're going to set the bandwidth to 2500 hertz. And the reason we're going to do that is the modulator that we're using, which is software written by Joe Taylor, I forgot, K1JT I think it might be, WSJTX software, they define their modem performance, or the DMOD performance, in a 2500 hertz bandwidth, not in EB over N naught width, which is normalized energy per bit. So let's work this out. We know what our signal power is, we know what our noise power is, and we realize that our signal to noise ratio is minus 17.6 dB. Well, that doesn't look very good, but since they do this thing in 2500 hertz, the detection threshold for that software DMOD is minus 27.6 dB. So therefore, we've got about 10 dB or so of signal to noise ratio that we can actually work with. So how does it work? So we're going to go and take my receiver. I'm going to compute the equivalent noise power that's going into the system. If I've got that equivalent noise power, I know what the signal power is. Let's see what the degradation of my receiver looks like. And let's put it all together and see what that signal and noise ratio turns into. So we do a little bit of math. We do the LNA, which I have in front, it's 0.33 dB noise figure. The rest of the receiver is a 2.5 dB noise figure. That's taken from the 809361 data sheet. I've got a cascaded noise figure of 0.331. So notice what happens. I got a 0.33 dB noise figure, and I've got 35 dB gains. So I don't degrade the system because I have that much gain up front with a low noise amplifier. So the equivalent noise power is calculated. I'm now in the order of 10 to the minus 19 watts. I now work out all the noise contributions to the system. I know the KTB noise in the system. I know my receiver noise. I know the sky noise. I talk to the astronomers. 1296, what's the sky look like? They say it's about 10 degrees Kelvin at that frequency. And then I have a system noise temperature. It's a bit of a place where I catch it all, but what happens is my antenna illuminates the ground a little bit, so I see some ground noise behind the antenna. I know what's the illuminating factor on the parabolic antenna? Okay, so I estimate that, and I put the whole thing together, and I say, okay, I'm going to have a final signal noise ratio of about minus 20 dB. Let's see how that works out. So now we build it. So the first thing you do is you get a GNU Radio, right? So you put it together, Osmocom source, Blade RF talks to that, do a little frequency offset control, do some decimation. In my case, I've got the receiver system outside, and inside I've got another instance of GNU Radio, which is now going to feed the data from over a UDP socket going over an Ethernet going outside into another instance, do a little bit of filtering, and feed it into WSJTX, which has got to be connected to an audio device. We have to do a little bit of hand waving to get the audio from GNU Radio into WSJTX. And guess what happens? We listen to somebody. So here we are after all this work. If you look in the little ellipse that's in about the top center of the screen, you can see this little tiny trace. That's the actual carriers coming in from the received signal. And you can see it's synchronized in 1 minute intervals. So we calculated that we were going to be at minus 22 or minus 20 dB, and there's a signal noise ratio being copied. WSJTX calculates for it, and I'm reading minus 22. That's not bad for system engineering. With all the assumptions that we made in the system, we know our gain, we know our LNA noise figure, we know all the systems, we're estimating the moon distance, and we're within about 1.5 dB. It's pretty good. So let's see what happens. So let's take a look at how we do the hardware. So this is the hardware side of what we put all together to make this happen. So the first thing was built an LNA. So anybody who's into the design world sees that that's an ADS schematic, and I designed the LNA for it, and we predicted that we had a reasonably good noise figure. I think we predicted 0.28 dB noise figure and 37 dB gain, and I don't know if it shows it on the bottom of the, there it is. So there's the built unit, there's the measured in the lab. We simulated 37, we got 36.9. Noise figure, simulated 0.28, we got 0.329. Not bad. What's the antenna look like? So there's a 2.4 meter folding antenna. There's the LNA. There's the feed assembly all sitting on it. It's circular polarization, so we have a 90-degree splitter in it. There's the receiver. So if you look at it, you can see a blade RF. There's a little kind of NUC-type computer. There's the GPS receiver sitting there. And sitting in the back, there's the tracking controller, because I got to keep the antenna pointed at the moon. So that's what we put together. And then for the transmit side, when we were looking at, that's the driver, and there you can see actually a two-tone intermod measurement. If you look in the spectrum analyzer, you see the two carriers they're coming in to test it with, and those are the intermod products. You can see the third and the fifth intermod products. And there's a Pluto actually generating the two-tone signal. So you can use a Pluto or any other thing as a two-tone test generator. Put up two carriers, feed it into GNU Radio. There you are. You can see the flow graph there. All right, there's a power amplifier. For me to transmit, I transmit with 500 watts. So one big transistor does 500 watts, 50 volts, 20 amps, about 1,000 watts in. There's it on the test bench running at about 500 watts. So real radios are written in C, Verilog, Python, C++, Rust, pick your language. I don't think they glow in the dark anymore unless it's LEDs. So software, what we did outside, I think I've got about 3 minutes. What I did there is I have the blade RF. In the software side, I sample it, I do a digital down conversion, and I do a frequency offset because I got to do a fine frequency correction. I want to be coherent while I'm doing it. WSJTX computes the Doppler shift with the moon, so I got to feed that into the system, and I want to do that with a DDS. If I tell the RF to change frequency, it will sit there and has to relock, so there'll be a big frequency bump when I do that. Let's do it in the digital main. I do 2 stages of decimation going down, then a complex FIR to make essentially an SSB receiver at about 3 kilohertz bandwidth. And then I feed it at 48K samples per second via UDP socket. Transmit side, it's essentially the reverse operation. Okay. On the inside, where I bring it in, I go through pulse audio. Pulse audio is the shim that I use to connect between a TCP socket and WSJTX. WSJTX software wants to see the world as a sound card device. I can't do it any other way very well. So I have to come up with some shim. Fortunately, the pulse audio guys made enough things work, so it goes, and there it is feeding it. Okay? So it'd be nice if it had that. Unfortunately, that's a de facto modem interface. That's what we use. Okay? Transmit, receive control. There's a lot of stuff in the back end that's got to go. When you want to go from receive to transmit, turn off the LNA, switch the antenna, turn on the power amplifier, turn on the driver, turn on the envelope, and start transmitting. You want to go back to receive, turn off the envelope, turn off the power amplifier, turn off the driver, switch the receiver, the antenna back over to the receiver, and then turn the LNA back on. So you don't want to transmit 500 watts in the LNA. It won't last very long. Okay. So we have the little block diagram with the frequency control hall that was all set up to go together. WSJTX talks to the HamLib system. I had to write some code to actually interpret that, so we built an interpreter for it. We built a little state machine to do the frequency control. We had to go and extract the TR control out of that, and then add a little monitor widget to actually control it. So, any questions?
All right. Let me just come over with the mic. Excuse me, I need to squeeze through here.
Hi, is there any special reason for the choice of this frequency, 1296 megahertz?
It's one of the frequencies where all the people who want to talk to the moon use. So there's a couple of frequencies we use. It's usually 1296.065. There's a kind of a chat reflector that's online. We all kind of gather on that, and we decide what frequency we're going to go on and what kind of timing sync we're going to use. And there's multiple modes. Since the WSJTX modem has multiple modes, we select which mode we want to try. Okay, so that's where the one. There's also activity on 144 megahertz, 432 megahertz, and then 10.368 gigahertz. And there's some other ones in between that aren't as commonly used, but 1296 and 10.36 gig and 144 are fairly common. Anything else?
Actually, the next speaker here, Francis. Okay, you can already walk up. Oh.
Just for perspective, where were you located and where was your friend located?
I'm located in Portland, Oregon, and he was in San Diego. So we weren't line of sight. Except via the moon.
All right, thank you very much. We will thank the speaker again. Thank you, Dennis. And what?
Quick announcement, we have 2 pairs of sunglasses that were left at the social last night. They're at the front desk or the registration desk if you need them.
All right, protect your eyes and also, stay hydrated. Okay, so we went to the moon in the last talk, and now we're gonna go billion years in the past or something like that. So it's getting more and more extreme. All right, Francis, take it away.
Hi, everyone. I am Francis McGee. Oh, this one slide too far. I am Francis McGee. I am a graduate student from McGill. I'm working in the lab of Dr. Cynthia Chang on early universe cosmology, experimental early universe cosmology. So I'm here to tell you a little bit about our antennas, our system, how we're using more conventional radio stuff, and how we want GNU Radio to be involved in our system later. So my work that I've been doing has been alongside a pair of undergrads, Michael Haytu and Vlad Kalinescu, who played a big role in this, so I want to shout them out at the beginning. So I'm just going to give you a quick overview of where our antennas fit in kind of the grand scheme of the universe. So as you probably know, early on there was the Big Bang, and then after the Big Bang there was a lot of ionized matter that then recombined into kind of a neutral matter, which doesn't give off a lot of light. And then we had an era of reionization that gave off a lot of light, and then we have the galaxies, which give off a huge amount of light and get in the way of all of the measurements of that stuff before. So our system is set up to measure 2 different parts. We've got 2 different antennas that are measuring 2 different parts. We collaborate with a lot of groups, but these are the kind of the 2 ones that are under active development that I've been working on. There's the albatross antenna and the mist antenna. And the albatross antenna is mainly used to probe the cosmic dark age, and the mist antenna probes a little bit more kind of around cosmic dawn when the first stars are starting to appear and reionization is beginning, and probing a little bit of the dark age, but not so much. Now, with the dark age was dark, and it didn't give off a lot of the kinds of light that we would use to probe other periods of time. So there was a specific hydrogen transition called the 21 centimeter line, which gives off a distinctive 21 centimeter wavelength line, which is then redshifted as the universe expands. And by measuring this at various kind of modern wavelengths, we can see how intense that line was at the universe in previous time periods. So we're looking very much at that early part here, the very early part, and all this stuff in the middle is kind of getting in the way. So I'm going to tell you a little bit about the early albatross antennas. So this is our kind of the base antenna that we use here. This is set up just kind of in a remote location. These albatross stands for Array of Long Baseline Antennas for taking radio observations from the 79th parallel. That last word has changed a few times, but right now it's 79th parallel. And this is, as I said earlier, a probe into the cosmic dark age, which happens at a wavelength that's interfered with heavily by modern civilization wavelengths like shortwave radio and things like that. So to do this, we have to go far away. That's why 79th parallel, it's way up in northern Canada is where we put our antennas. That's why McGill is uniquely positioned for this because we have a lot of access to these northern areas where we have our Arctic research stations. So I'm just going to give a quick overview of how our system is set up. We do not have the kind of a GNU Radio software-defined radio working in this system. This is kind of a more traditional radio setup where you've got our large antenna, we've got just the usual filters, amplifiers, a custom kind of, it's called a snap board. That's been used in this project. It's also been used by a few projects here at ASU. And then the data is sent out from that into a set of hard drives. Now, this is unique in that it needs to last through the winter. And as you probably know, the winters in the Arctic are not as easy to make things last in as summers in a lot of other places where they do radio astronomy. So unlike a lot of other systems which would either have some kind of power connection, which is impossible far away, or run off of something like solar, which works great for something, say you're in the Australian outback, that's perfect for solar, maybe with a bit of a backup for nighttime. But for us, we don't have light, we don't have heat, we don't have ability to access any of these things, so they need to last throughout the winter. And the way we handle this is we have a hybrid fuel cell solar panel array. And this is set up with my colleague Ian Hendrickson here, who was setting up and helping to set up some of these antennas. And you can see in here, in the bottom right, that that's the fuel generator, the fuel cells. And down there is the front end box, which detects information from the antenna and then stores it to a hard drive array. Now, one of the big things we're aiming for with this project is to keep things off the shelf, keep things open, keep things accessible to others, so that first of all, it's easy for us to scale up this program so we can have more and more antennas as we need them, and also so that it's easy for others to verify and reproduce what we're doing. So we're trying to have a kind of a minimum of, this is a $500,000 custom piece. So I'm just going to give you a bit of context as to where exactly these are located and where we work on these. The first place is Uapishka, which is in the interior of Quebec. It's fairly far from civilization, but it's not completely disappeared from civilization. So we can drive up there pretty much all through the year, not completely, but it's accessible. So we can set things up for testing, we can run things in a fairly radio quiet area, but we also have up on Axel Heiberg Island the McGill Arctic Research Station and our actual antennas in a very, very radio quiet place that's not accessible outside of a very narrow window between the very early summer and midsummer, because Arctic summer is very short, but it's the time we can go up to access it. So we've also got a second antenna that we're working on called the Mapper of the IGM Spin Temperature, MIST, that's again probing the dark ages, cosmic dawn, and this was designed to verify a previous measurement called the edges detection. And one of the things with the edges detection is that there was some discussion that it could possibly be the antenna backplane, which caused some interference with that detection, and we want to verify if that signal was true. So to do that, we are now building this new MIST antenna, which does not have a backplane. So because of that, and this is where GNU Radio is going to start to come in, we need to know the soil properties very closely. And one way to do that is with soil probes. Those are a little bit difficult and not always consistent. They're kind of destructive a lot of the time. So we are trying to work with ground penetrating radar systems. And we want to get something that is open and usable for other cosmology experiments, other glaciology experiments, and other experiments where they're working in very rough terrain, and the commercial closed source systems are not really viable alternatives in the way that you would like them to be. Because a lot of these closed source systems are very bulky, they work at one particular type of frequency, they run on proprietary software, and most importantly, you'll remember in the Arctic, in the winter, it's a nice kind of snow, nice. It's a nice snow. And if you want to do glaciology experiments, you can just slide your GPR over it. It's great. But for us, when we're setting things up, it's not always the winter. It's the summer. And in the summer, it's rocky, it's craggy, things are kind of half melted. There's things that used to be frozen ice kind of cracking. So it's not, even this cart, we have one of these carts that we've attempted, and they're not really capable of getting the measurements we want to be able to nicely figure out those soil properties. So we've been working on building our own GPR that we want to mount then on our drones, because we use drones for antenna characterization. So we basically want to see what the beam pattern looks like. We have a drone that flies around and basically detects how it can interact with the antenna. And we've already got this set up. I'm not sure if the video is going to play on this setup. No, it is not. Well, as you can see, pretend there's a very pretty video of a drone flying around, and it's going to show you the kind of Arctic tundra. You can see how it's very not sturdy. It's not like going to like Death Valley or something. There's a lot of antennas they like to put out in places like Death Valley where it's very flat and easy to just run a ground penetrating radar or lay out a network of soil probes. It's not so simple up in the Arctic. So there are and have been ground penetrating radar drones. We've seen them. Most of them are closed source or use extremely expensive equipment, which is not the goal of this project. The goal of this project is to make something that's accessible to people. So say any other group that wants to set up its own ground penetrating radar drones will be able to do this. So we're doing this completely openly. We want to have this completely accessible to people, which is why we're using the EDIS platforms that we have, because those are open and easily accessible, and if we publish the code, anyone can grab one of those, replicate our antennas, slap them on their own drones, and they'll be able to replicate what they've got. So this summer, I was working with the pair of undergrads, as I was discussing, on testing GNU Radio. GNU Radio is new to our group. This is kind of the first summer that we've been playing around with it. We got ourselves a B210. We've been kind of trying to build a initial prototype of just a non-drone ground penetrating radar that eventually we're going to be able to put on the drone. There have been groups, as I said, that have done this before. We've adapted. This is just our very basic testing script. This was working with these undergrads this summer on this project. And we're just doing very simple here, just sending out a chirp through the B210, transmitting it, receiving it, and storing it. And then I wrote a little backend that will just do, it will just detect the transmit receive and detect, using match filters, the actual delay. So here is our setup. And Michael built this wonderful antenna setup here that's all 3D printed, all put together. We got our specific antennas that we've now brought out and tested on real soil and real conditions. And we've gotten some detections. We don't think they're quite ready to show, but we do have kind of a semi-working ground penetrating radar. So what we're going to show here is we've just got some loopback tests that were written by one of our undergrads. And these loopbacks basically are proof of life that the GNU Radio thing is working for us. And this is new information for our group. So what we've got here is just initial loopback tests showing on a quick, like a terminating loopback, and then a 20-foot cable, and then a 40-foot cable. And we're seeing the expected delay that we expected to see. So this has been kind of the project that we've been working on to get ourselves acquainted with GNU Radio and get ourselves ready to start using this either in our ground penetrating radar or eventually in the back end for future radio telescopes, because it's a really nice extensible way of keeping things open while also making things more accessible to new people who are getting involved. Because previously, to get someone up to speed, we had to go through a huge amount of manual components, which is difficult for getting people up to speed quickly. So thank you. Our next steps are that we're going to get the permittivity and conductivity extraction from our custom data set. We're going to try to miniaturize the system a bit more. Trying to get the B210 onto the drone is a bit iffy. It's definitely possible, though. We've seen some other people who've gotten it on in other contexts. And we're trying to get a full like step frequency continuous wave implementation going that we can definitely say with testing is giving us good ground penetrating radar results up to par with the commercial units. Because right now we've got initial data that's working, but not quite commercial grade yet. And then we're going to field test it, hopefully in the Arctic. So thank you. If anyone has any questions, I'd be glad to answer them.
Thank you for mine. One sec, is Henning already here? There you go. You can already walk up, but we'll take a question or two. Sorry, I saw a hand. That's Kevin. What frequency is what for the ground penetrating radar? Oi. Oh, yeah.
Oh, for the antennas. The antennas are working around 1.2 megahertz up to about 200. So it's kind of that range.
And is that like the redshifted frequency of
That's the redshifted frequency that we're looking at, because we're trying to look at each antenna looks at a slightly different frequency range, but generally that area.
All right. Anyone? We can have one more question. I'll take Libby over you. Sorry, and Henning, you can go up and set up.
Thanks. How much of the dark ages are you actually able to look at? Like, how far back do you get? Because I know at some point the ionosphere starts blocking and you're not able to observe, and that's why like far side and stuff is a thing. So like, what's your redshift expected?
We're still not fully getting a result from that yet. I don't think I can speak to that very well. I'm more on the ground penetrating radar side of this to be able to answer that question.
Cool, thanks.
Thank you once more. Thank you one more time, Francis. Okay, and next up we have Henning from Germany, who will be talking about receiving ALS 162. And if you don't know what that is, Henning will tell you in just a second.
Yeah, thank you. So hi, my name is Henning. So I'm actually some kind of an amateur here. So well, I have a background in information theory and also in cryptography and IT security, but that doesn't matter that much here. So here, just consider me as an amateur. Yeah, so I will just go one ahead. So I will just go through the transmitter, the channel, and the receiver briefly and show you what it is, but you can sit back and relax. It's pretty basic. It's not something complicated. And I actually hope that one will use it later on, maybe for a lecture or something. Yeah, that would be great. So, okay, what is ALS? Well, it's the Alois transmitter in the center of France. You maybe see the red dot there. Unfortunately, you will not be able to receive it here. It's just too far away, unfortunately. So it's been on like for several decades already. So it's it has been transmitted since 1980, and it's driven by a cesium atomic clock. And you will receive it at a frequency of 162 kilohertz, which is pretty low frequency. It has a relatively small bandwidth, and it's pretty strong. So you can actually receive it about 3,500 kilometers from there. So that should roughly reach maybe Iceland and Greece on the other side. Yeah, and that would be about 2,000 and several miles. But you will not be able to receive it here in Phoenix, certainly. It's a phase modulated signal, and yeah, that's about it. So I can receive it pretty well in Germany. It's not too far away. So, okay, this is how the signal roughly looks like. So this is one part of the signal, of course. So on the left-hand side, you see this kind of triangle up, triangle down, and then just a flat line. So that's basically a binary 0. Then you have some very strange signals. We ignore them for the moment. And then in the end, we have like going up, going down, going up, going down, going up. That's a digital 1. And you have just an entire second covered by like from 0 to 1,000 roughly in this graph there. Yeah, so those will be the bits for each minute. So you will have 60 bits in total. And then there is this very strange stuff in the middle that's actually not specified in any, yeah, there is no specification for that, but I realized, okay, that's apparently the second, so you can actually find, you can see here, for example, that's the 47th second in the minute, so I had to actually brute force that one out of the signal. Yeah, that was I needed quite some time to find that out. Yeah, so if you look closer into that, you will see that like the slope of the signal is like at the first it's +1, -1, -1, +1, 0, 0. Like if you look at the start, we will actually use this kind of derivative signal later on. Just keep that in mind, please. So yeah, that was basically the transmitted signal. So that will be received then later on. But first of all, let's take it through the channel. That's a pretty basic channel, and it actually resembles the actual channel. So you see this is just a simulation, but the real signal looks pretty much the same. Yeah, so we'll have the signal that we've just seen. It's submitted on the frequency or modulated up to the frequency of 162 kilohertz. Then there will be a slight attenuation, of course. It's basically pretty slow fading. You hardly see any difference over several minutes when it comes to the strength of the signal. Then we have, at least in my case, I received some independent impulsive interference. So just like this kind of, well, it looks like a heartbeat signal to me, actually. So we see some kind of spikes, and those interferences can be somewhat disruptive sometimes. Yeah, and then of course we have noise. So I will not show you the flow graphs for that, but if you are interested, you can of course look into the repository for that, and into the flow graph of GNU Radio Companion. So okay, now the interesting part, the receiver. Okay, there are several steps to be done. And I think most of you have seen such steps already, so I won't go into detail for each of those. There is the demodulation step. Well, that's pretty straightforward. I hope each of you could do this just by hand, just in a couple of minutes. Then we have time downsampling. So I'll just use the downsampling module of GNU Radio. That's also pretty straightforward, just to reduce the complexity of the signal, of course. And then it gets interesting, because it's a phase-shifted signal, so it will drift off slightly, and at a certain point at pi, it will just drop down, and this is pretty bad for reception, so you have to compensate for that drift. And at first, I didn't know how to do it. I knew there is some kind of phase-locked loop, and there are several components, but I didn't know how to use them, so I started to write my own kind of drift compensation, and let's briefly look into that. So I want to get rid of those spikes at pi and minus pi. So I simply computed the average over a longer time so that I can see, okay, there is a mean value is raising, and I simply subtracted from the signal itself. It's pretty clear, and it works. So the blocks are just seen there. So I waited a little bit so that it's not like heavily going down, but it's like smoothly staying like on the line, and we will see the signal as we want it. Later on, I realized, okay, I could also use the PLL carrier tracking block with a very low frequency. But, well, you learn afterwards, and this is what I wanted. I wanted to learn something from that. So if you want to download it and play it, you will see that you have to change the parameters a little bit so that that it fits and that the phase is actually compensated. So I can't take a parameter for everyone, so it depends on the CPU of your computer. So furthermore, the next step is, okay, I have to synchronize the signal. And I took it into like a separate block that I wrote in Python. And I basically just count the samples, and I know that the difference between those ups and downs in the signal, that there are about 25 milliseconds, and that I can simply take some kind of tolerance part, and as soon as I reach tolerance and the signal changes, I can see, okay, this is a 0, a 1, a +1, a -1, a +2, a -2. You can see this on the graph on the right-hand side. We have the phase signal, and we have also the derivative signal there, and it apparently works pretty well. So like we have a small +1, a small -1 there. Yeah, so I implemented that as well. I see that there is also some kind of synchronization block in GNU Radio Companion, so it could be an interesting idea to replace that block that I wrote there with this other block, but I didn't do that yet, but it works pretty fine anyway. The next step is, okay, we have, I actually want the binary signal of the 0 and the 1. And I just got some values like +1, -1, 0, etc. So I actually have to correlate those signals with the known signals. And then I get the signals that I want, both the signals for the watch, so for the time, and also those seconds, those slightly more difficult signals to discuss. Yeah, and I have to do this like for 59 seconds. And when that is done, I can actually decode the entire signal, and then we have a very typical time signal. So the next part is actually not GNU Radio anymore. It's just an ordinary Python script where I take all the bits, I look at the specification, and then I get, in this case, 12:37, I think. That's just the best time to use GNU Radio, I think, on Sunday. And yeah, it was a Sunday and so on. So it worked pretty well, and I even could include some error correction, because if I have some single bit errors, I also have a single parity bit in that specification. So this is usually not as sufficient to correct the errors, but in this case, I have the position of the error. And if there is only one error, I can easily correct it. That's a great thing. And yeah, that in the end, I have a nice signal. I have decoded it. It's human readable, and the decoder is basically done. So the entire thing looks like that. I have the GUI, and you see on top, this is the complex baseband signal, which is not yet represented in the phase representation. Yeah, and then we see the second part of this plot. We have the actual phase representation, and all those +1s, -1s, etc. And you already see there, okay, there just in the middle there's apparently a 1, and then there are some symbols that represent the second. Down there we have those parameters that you can change, and especially those ones that ensure that your phase doesn't drift away. Yeah, and on the right-hand side you see just a couple of zeros and ones received over a minute, and 1 minute that has been decoded. So what are my insights there? Okay, that's a pretty basic signal, but well, there are some challenges inside that, and it's great to learn more about how to work with GNU Radio. Those code words for the symbols for the seconds had to be brute force, because they were not specified. That was also an interesting experience. I needed like 3 or 4 hours just to count all those zeros and ones in that signal. Yeah, then I had the antenna. I just fixed it at my window. It's a loop antenna. And I had to ensure that it's really fixed and it shouldn't move or something. That's pretty important, that you get a really clear signal there. Okay, what else? It suffers from interference. I don't know where it comes from. Maybe it's a strong power line just nearby to my house. I don't know. Sometimes there is no interference at all, and it's pretty clear. You've seen the pretty clear signal just a few seconds ago. Yeah, I've seen that the derivative filter is good and it works, but it's not the best one. So I don't say this is a perfect receiver. If you guys here write a better one, I would be happy that you show it to me, and yeah, write a cool receiver and let's talk about it. So I think that's the idea of open source. I would be happy just to get in contact with you. Yeah, what else? I also did quite a bit of testing. So as you've seen, I've also written the transmitter and the channel. And in the end, I also built some kind of CI around it, so that this is really well unit tested, coverage tested, and each time I uploaded it to GitHub, it will work fine and go through all the tests. I think that's nice, because I've hardly seen that in any other projects yet. And I think it's important to have like a quality result there. Yeah, so far so good. I also wrote a paper on that. Please read it. Feel free to contact me. That's about it. My repository is seen there. Are there any questions? Thank you.
All right. We can have one question. Yeah, I have a question. How does this compare to, you know, DCF 77 and what's it called, WWVB? Is that right? Like, are they basically the same, or are they completely different? Do you know? Like,
well, this one is pretty quite a bit different from the German signal, which is more an on-off keying signal. so I've also a version of that in GitHub. I don't know the American ones. This is actually a challenge that I would like to propose to you. So if someone is happy to implement the American version of a time receiver, please feel free. I want to know it.
Has someone built that, or just Kevin? Yeah. Okay. Well, there you go. Speak to. And I just gotta say, I thought it's really cool how you use like stream tags for annotating the bits in the time domain signal. Is that how that worked, or because you had like all the bits, like the symbols annotated in the time sync?
It's just for the so the tags are just for seeing it in the plot.
But I think I thought it was really cool. It looks, it's very insightful. Like you can see like the waveform, and then you have like the values right next to it. And I mean also I mean I hate to pull out the stereotype, but your German meticulousness in like documenting or like putting like comments under all the blocks, and it was very, very cool. Like it's very it's like yeah, like Jean-Michel has does that too very well, where he has like just everything is just very like there's nothing is left sort of in a hand wavy state, so you can like completely understand everything just by looking at the flow graph, and in your case even the signal. I thought that was very cool. Anyway, another round of applause please, and our next speaker, Jonathan. Is he here? Oh, there we are. Okay. So I always walk away from my schedule, so I don't know the title of your talk, but it's right up there. Open source antenna pattern measurement. Excellent. I'll just so you have a demo. Okay, I'll just leave the stage to you. And
Okay, thank you very much. My name is Christian Hearn. I'm at the bottom of that list. Matthew Finger was kind enough to return as a graduate student. He spoke here last year and introduced our open source antenna pattern measurement system. And I'm here predominantly to just give an update on how it's being used and whom we are collaborating with as a result of it. And if all goes well, we will give a quick demonstration so you can watch what it does. So, which way do I want to go here? Plus, no. I might need some help. Which button? Which button do I need to do? Oh, that's why. The wrong handheld. Thank you. Okay, so. Okay, so quickly, this program, I'm a faculty in Weber State University. It's a small electrical engineering program, and my focus has been predominantly to increase our measurement and capability for our undergraduates. And this hardware demonstration that we'll conclude with is a result of two programs, or to say funded awards, from the Utah NASA Space Grant Consortium. I'll give a quick summary of the collaborations. Predominantly the Naval Surface Warfare Center, Lucas Ians, who is a regular attendee here. Keomac is a contractor that is located near Ogden, and Wireless at VT. I have a colleague from my alma mater who is using a version 1 of this hardware. And I'll quickly conclude with future directions and future collaborations, hopefully with John Kraft of Analog Devices, whom we met here last year. Okay, quick background. These are similar to what Matt presented last year, but in summary, it's a low-cost open source antenna pattern measurement system that was based on an IEEE paper that used Linksys routers and pretty much equivalent to Home Depot hardware. We took that idea, rebuilt it, and had the same problems that they did, and then upgraded with going to software radios, GNU Radio Companion, and we what was not around when the original paper came out were the 3D printer hardware, namely the synchronous belts and the synchronous gears that are available and ultimately low cost. Also, we have some custom-made 3D printing hardware pieces, namely this masthead here that I'll get a picture of in a minute, that have been developed, student-designed, and student-built in our engineering programs. And so there's a good picture of our version 2 hardware that's identical to this one here. You can see it's basically driven by stepper motors. This one is a single, this is a single motor control in the azimuth plane and manually controlled in the elevation plane for simplicity. And we use Arduino with Arduino as a motor controller for the single stepper motor control. We're using Hack RF radios for the RF link, and those are a couple of pictures in the middle of the SolidWorks designs that were developed in Weber State. The picture on the right is the permanent, the one that doesn't go on travel, and I basically modified a shop cart and integrated it so and kept it in what will ultimately be our anechoic. And that one, we made a couple of small changes, but all of the hardware is the same as the one we're going to show you in a couple of minutes. Just a quick look at the block diagram. We have the system is driven by a single PC, and we have two software-defined radios for the RF link. We have discovered along the way, we use AM coherent modulation for our test signal, our source signal, which is easily achieved with just tying the two clocks together, and that's sufficient for for this measurement. And then we have the motor controller side, which is driven, as I mentioned, by an Arduino with a GRBL shield. And we're using GRBL 1.1F. We have been for several years. And this block diagram shows both elevation and azimuth control. We only have azimuth control, one single stepper motor. That's just a quick multi-sim demonstration of AM, a coherent AM signal simulation that we currently use for this deployable open source antenna pattern measurement system. Along the way, Matt, who presented last year as an undergraduate and then worked for L3 last semester, and I'm grateful that I have him back on loan to complete a master's degree. But he started, it actually was a Python 2 version where he began to explore transitioning the software from Python 2 to Python 3, and we are ultimately now on Python 3.9, and we have, been users of GNU Radio since the version 3.7, and we're currently on 3.9. We had, I think it was a generation 3 Linux that was, when Matt finished last December, we were using a version 4.19 Debian. We've since moved on to Ubuntu because we have a Linux lab and my colleague, Jonathan West, who is very efficient in Linux programming and was a great help in May in finalizing the improvements to the version 2 software. And again, the GRBL is the open source industry standard for industrial control. This is a kind of summary of my colleague Jonathan West's contribution. Basically, one of the biggest hang-ups, and I've heard discussed a couple of times this morning already, was the sockets. The original software was, I think, a version, the Linux, it was a version of Python, and it still used a socket, and we were having big trouble saving our data and into a plottable format. All of that is now eliminated in the version of software that we have on a GitHub repository that I will make open after this conference today. Does not use the old socket, and it is much more efficient than it had been. And the other thing that Dr. West was a huge help with was the creating JSON files to make global variables, and you would go in and basically, we don't have it quite menu driven yet where you're asked for frequencies and number of points, but it's still kind of a batch file format, and it's an infinite improvement from what we had before. And again, the GitHub is kind of a new parameter for me. I'm more of an electromagnetics person who is learning Python on the fly, and but it is definitely the wave of the future, and I have the collaborators that I will mention on the next slide have at least access to the GitHub, and I will make it open directly. This is a slide that just shows the mechanical design of the 3D parts that we've been using in-house, and almost all of these were designed and built by undergraduate students. I'll shift now to the collaborations. Last spring, or I should say last year at the GRcon23, we met Lucas Ians, or I should say Lucas Ians met Matt. I was not present at the time. And last May, I delivered a prototype to him. I learned some pretty painful lessons about shipping this on air travel, so I'm still keeping my fingers crossed that everything will behave for the next few minutes. But to the best of my knowledge, he has still been using it, and he mentioned to me that he is working on a GUI interface at this point. The most recent collaboration is a contractor, Keomac, that is centered in Virginia, Reston, Virginia, but they have a large presence in Layton, Utah, which is just outside the Hill Air Force Base, and we are evaluating integrating arrays to drone wings, and that's a little picture of a half-scale drone with some patch antennas just for proof of concept demonstration. The third collaboration is with my colleague Carl Dietrich at Wireless at VT, and that's a version 1 prototype there. He has a chance for a funded senior project this fall that hopefully will be using this system, and I'm going to probably deliver one for him so he doesn't have to deal with a wooden sawhorse that looks like it came from Home Depot there. Circling back to Matt Finger, who has returned as a graduate student with a NASA graduate fellowship. Our plan this fall, he just returned 2 weeks ago, yeah. And our initial plan is he's going to reproduce the digital beamformer that John Kraft, another person we met at this conference last year, with the Plutos, and we're looking also at wading into radar systems and radar signal processing. Wrapping up the slide part of this, and we'll shift to the demonstration in just a moment, but I would like to acknowledge the Utah NASA Space Grant Consortium that has awarded this effort twice. Moog Industries donated the absorber that we are using, and certainly my acknowledging the contributions of my students along the way, Dan Newton and Taylor Hansen and Ren Fisher, and of course Matt Finger. With that, I think we will give this a go and demonstrate, and if we could get this, push the right button, there we go, if we can switch to this. I'll let Matt do the talking.
Perfect. Like you said, my name's Matthew Finger. I'm just a graduate student there at Weber State. I'm just going to do a quick demonstration on our machine here. As of right now, it's very terminal based, kind of bare bones, so that if we want to go back and change anything, we can at any point. We got a couple of different options. So the first one is the one we'll demonstrate, which is just a fast scan where we sweep all 360 degrees in one quick motion. The other ones are a bit slower. They take about 10 to 15 minutes, so won't be demonstrating the day, but they are the ones where they will go to an angle, read that direction, and then, yeah, the fixed direction, and then move an angle, repeat all the way for the 360 degrees. Yep, so we can plot multiple traces or kind of compare it to our fast sweep. Cool. So at the very beginning, it's going to go back to its 0 position, so that way it's set every single time, and we will get the full 360 degrees. Once it hits the 0 position, the transmitting antenna will start transmitting, and it will start reading and do the full 360 degree sweep. And as of right now, we are on 2.4 gigahertz because it is very easy to build those antennas by hand, and it's a lot easier to test in a campus and student environment. So as of right now, the receiving hack RF is active, as well as our transmitter. We're spinning our 360 degrees. It's getting our data points for our measurement system. Once it hits at 360 degrees, it cuts off the transmitter and the receiver, saves all the data points, and sends us back to our 0 position. So that way it would be ready for the next scan, or if we wanted to do a different antenna. And this one that we're testing right now is a directive Yagi. It's what, 4-element? So it's a 4-element Yagi. And we have just kind of a plot there. Let me shift that over. So there's our just raw data points that we can see from it. And we will go in here in a second and look at it in our polar version and convert it to dB. So we'll go to our 4th option here to plot our last run. We'll say GNU. And it will ask us if we want to plot it in dB or versus just raw magnitude. So we'll go plot in dB. And we have our plot, so we can see our frontal lobe is very directive in that very first direction as we're kind of looking down, which you would expect from a Yagi. And then we've got some kind of side lobe action, and most likely from some bouncing off of either the ground or the wall here, because of course this isn't an anechoic chamber, so you're not going to get 100% perfect result, but you can get a visible demonstration of this Yagi is going to put most of its energy in that direction. All right, thank you.
Thank you, Matt. Yeah. So, are there any questions? I guess I just want to mention, I want to thank the GNU Radio Companion community and this conference that's definitely and broadened our horizons, and we've made some very valuable contacts, and definitely has breathed some oxygen into my research and scholarship efforts, and hopefully building a EM and antenna program at Weber State University. So any questions? Yes, sir. Oh, probably need a microphone.
No, I'm right here. Hi, this is very cool. So I'm a grad student up at Penn State, and we have an anechoic chamber. and I had to completely rewrite our software because it was terrible. And so I've done a GUI for doing pattern measurements. Would love to talk.
Sure.
Did you explain if you had a way to do any kind of calibrated measurements, like realized gain?
Right now, I'm just promoting this as a relative measurement, a student tool. We're in a brand new building, and they've given me space for a chamber. It's not outfitted yet, but everything this past morning and afternoon, I recognize that calibration is something both in where Matt's going in the future and where we are now is something that we want to have to pursue. But right now, it was really just a student tool, to give them an access, the idea that students who are better at software can get introduced to antennas. Myself, an antenna person, can actually get something that works using these open source tools, but the accuracy is not there yet. So I probably need to talk to you.
Yeah, I would love to chat. I mean, still very cool to be able to get a student in their backyard taking a pattern measurement of some coat hanger that they made. That's very, very cool.
I agree. Thank you.
We can have more questions. We're a bit over time, but we don't have a talk immediate afterwards. Was there? Oh no, you weren't. No? Okay. Well, I also like the fact that you have like this completely open source set. I just love that. I just wanted to make, it's not a question, I just wanted to say well, I have the mic that I also think this is pretty
There's
cool.
a lot to keep track of, and Matt did a lion's share of the work, bringing that, was it from Python 2 to Python 3, and upgrading the GNU Radio companion at the same time, but he did a great job.
Well, I think for that he deserves a round of applause as a speaker. And
thank you.
All right, so we have lightning talks lined up at 1:45, but then we have the break. Should we just pull up the lightning talks? Is Josh here? No, he's not. So let me pull up the lightning talk schedule real quick. Because of course we can't start the talks if the speakers aren't actually here. All right, so Felipe and Andy, are you guys in the room? Oh, perfect. Do you want to start right now, and then we'll just do a longer break? And Andy, I just saw him walk in. So yeah, do you want to come up, do your lightning talk, and then we only have 2. If there's a last minute, any last minute interest in doing a lightning talk, go ahead. Yeah, this is your slide deck. Perfect.
Hi. My name is Felipe Taveiros, and I'd like to share with you today this use case of GNU Radio in our project, which is entitled Embedded Systems in Remotely Piloted Aircraft, SEARP. This project aims to provide long-distance remotely piloted aircrafts, RPA, video stream and control by using GNU Radio for a space launch operations facility in Brazil. Not this one? Oh, thanks. So, Barreira do Inferno Launch Center is the Brazilian facility dedicated to sounding rocket launches. It's a spaceport located in the city of Natal, state of Rio Grande do Norte, very near to the equator line. This name, Barreira do Inferno, literally means the barrier of the hell. It's a curious name with a fun story behind it. So the sounding rockets that are launched there, they go up a few tens up to a few hundreds of kilometers of altitude, and they fall in the ocean a few tens or even up to 100 kilometers distant off the shore of the coast. So this area that you are seeing is restricted. Although it's a restricted area, it is frequently present, we see frequently the presence of ships and boats disturbing the launch operations. So in order to keep the operations safe, we use airplanes with radars to scan the area before the operations in order to prevent the the rockets from falling off in anyone. So the usage of airplanes, conventional airplanes, and radars is very expensive. So we proposed a solution of using remotely piloted aircrafts in order to scan this area at a fraction of the cost of using, regular aircraft. So we then started to research project, development project, which we are using the Penguin B airframe, which is able to fly for over 20 hours and carry a payload of up to 10 kilos. So it's a very nice tool to perform the scanning of such a wide area, as you saw. But regarding to the communicating data link, there was no data link available off the shelf, which was able to allow us to control the aircraft in such long distances and to receive video streams of the area scanned. So there is where GNU Radio comes in. We had to build from scratch our own data link in order to provide that. So since it's a very quick talk, to make a long story short, we ended up developing this project. We came up with two proposals of data links, one operating in the VHF band in order to control the aircraft, and the other data link in the S band to provide real-time video streams. So it has not been tested in flight yet. We are performing right now static tests, but GNU Radio allowed us the flexibility to come up with our own data protocols and modulation schemes to achieve this goal of long-distance communications. So in the next year, we intend to test it flying, actually. So that's it. Thank you all for the attention.
Quick question for anyone? I'm sorry? Oh, do you have contact information?
Oh, sorry, I forgot about that. I can, my email is filipe.taveros@gmail.com. But I will talk to you later, okay? Sorry about that, I really forgot. Thank you all.
All right, thank you again. And Andy, you can come up.
Okay, before we start, so basically when I was talking about the WSDI platform, I mentioned web USB technology, and Mark came to me and said that I should say more about it and how we implement it and what's the beauty of this technology. So yeah, just wait for a second.
Do we have slides queued up for Andy? I don't know. I don't know where the slides come from. It's always magic. No, you don't? Okay. Is there a problem, or do you don't have the slide deck? Should we do coffee break now, and then you can fix? Okay. Well then, apologies to you. We have to fix some technical issues. Well, in that case, we will. Let's see. We will take a break now. I don't know if the coffee is already ready, but we'll just meet here again at 3:15. So 3:15 for Andy, and then we'll just move back into the regular schedule by then. Time. We're gonna kick it off with a lightning talk. This time we have it all running. It's working. Thanks, guys, for fixing the AV and slides. Actually, sorry, Bailey and other person. Can you two guys just close that door, please? Or anyone at that corner, it's fine. Mark's doing that, so we have the door closed. And yeah, we're gonna have one lightning talk about web USB, and then we start with the regular talks. Yep. All right, Andy.
Yeah, thank you so much. Thank you. Let's get back to the web USB and how we leverage this technology in our SDR. So as you may know, when you how the typical process working with the hardware looks like. First of all, you need install the driver, and most of the time it's not compatible with the operating system. Then you need to install the software, and for the software, pretty much the same problem. It might be not compatible with the operating system, as well as you need to compile from the source, and let alone of the dependencies. And needless to say that some software designed in a way to force you to download a lot of stuff, and it's became bulky and leads to the bloatware. Even if you have everything right, it doesn't mean everything would be work properly. So because of the specific settings that require software to interact with your hardware. So basically, you need to apply a lot of effort to make it happen, and make up and running a simple spectrum analyzer. When I was showcasing 2G cellular call based on a SMACOM stack, I was literally doing the simple stuff. I just plug in my USDR into a laptop, open the web browser, and that's it. So all the hardware drivers as well as the software were already integrated in the web browser. So basically, we make our SDR just plug and play. What else? Yeah, many projects, by the way, starting adopted this technology. For instance, Arduino, you can do pretty much the same thing, just plug the device and start working with it. So web USB might remind you a WebUSB API where you can control your device. Oh no, yeah, just WebUSB might remind you the WebUSB API where you can control your device at the endpoint level with some limitations. However, there's no timeout, and there's no USB request cancellation, so your logic implementation has to be altered in the way you do your integration. Of course, web performance isn't comparable with the native applications. However, WebAssembly allows you to your DSP work efficiently. So modern web browser can utilize multiple cores of your CPU through the web worker. And the recent web GPU standard provides general computation on GPU in the web browser. So performing task in the web browser, it doesn't look like a toy anymore. So this allows you to build a full-featured application in the browser. But WebUSB is not limited you to use in the web browser. So basically, you can run application in Node.js and even do your own standalone application. So we develop our platform, which leverage all of the standards just to make our SDR easy up and running, yeah, for you within a click. So here's the video where I transform my smartphone into the portable spectrum analyzer, pretty much next to nothing. I was using just a USDR and WSDR platform, and yeah, this is. Can I Just click it? Okay. Short video, just. So yeah, thank you so much. This is how you can leverage web USB in your application and pretty much like remove all of the drawback and drawback from your application and make it happen like easily with web USB technology. Thank you.
All right, thank you, Andy. And of course, he's around for questions. We're gonna go straight to the next talk so we don't slip too much in the schedules. Do we have the next speaker around? Adriana. Advancing ground station capabilities. Oh, I'm sorry, you're right behind me. Okay, grab the mic and.
So good afternoon, everyone. My name is Adriana Rivera. I'm a computer engineering student at the University of Texas at El Paso's Aerospace Center. So today I'll present on our work advancing ground station capabilities using a single web-based application for satellite tracking and communication. That is the outline that I will follow in today's presentation. So I'll start by giving a brief introduction about some concepts relevant to this discussion. We talked about Cubesats this morning. Reiterate, Cubesats are a class of nanosatellites. They're basically, each unit is 10 by 10 centimeters in size, which each unit weighing less than 1.3 kilograms. So they're pretty small satellites. And the fact that they're small makes them low cost and makes them have a short development period, which makes them attractive to a variety of sectors because it's a easier, cheaper way to prove concepts in space. So we at the Aerospace Center, we're currently working on a Cubesat mission called SleeperSat. This mission is scheduled to be launched in less than a year. The point is basically to prove the concept of rapid development of modular CubeSats. So in essence, you would be able to take any CubeSat module, plug it into another one, and they would be immediately able to communicate and work with each other in any configuration. In the development of this concept, we're also emphasizing digital engineering principles and techniques, so maintaining a digital thread of simulations, a digital twin is what we're trying to accomplish. What you see there is the model of our CubeSat. You can see it's a 2U robotic arm, just plugged in like Legos to other 2 units. And in essence, they should be able to work together and communicate without any intervention from us. As part of this mission, we're also developing our own in-house ground station. The point is to automatically track and communicate with satellites operating in UHF and S-band frequency ranges. I'll go a little bit about why ground stations are important for CubeSat mission success. So just by the nature of CubeSats, they face some challenges, mostly due to their small size. So since you have a small surface area, you don't have that many places to put solar panels in, so you have a limited amount of power in the spacecraft. So you have to be very meticulous and manage your power well. So you might prioritize certain tasks over communication, etc. Another thing is that due to the size constraint, you might not be able to place like antennas where you want to place them, where you have to be very like specific or smart about where you place your antennas, because most CubeSats don't have a dedicated propulsion system to like point the antenna towards the Earth or point the solar panels towards the sun to charge up, etc. So because we expect some like difficulties from the CubeSat itself, we want to make the ground station portion of the communication link as strong as possible. And this is why we want to develop our own. The objectives of our application are to enable live satellite tracking, manage real-time communication, implement seamless UHF and S-band signal decoding, and provide real-time display of satellite data, all in a single application. And I say within a single application because some previous efforts that we made in the past to make this ground station work included like running software on different machines or like compatibility issues between Windows operating system and Linux and certain components that we wanted to use. So this time around, we want to make everything fit into a single program. So I'll go over the components of our system. The hardware components, of course, are antennas. You can see in the picture there, we use 2 cross-polarized UHF antennas, Yagi-Uda antennas, for our UHF communication, and they're mounted on our S-band dish. To move those antennas, we have an azimuth and an elevation rotor controller, and we mounted the antennas on top of each other so that we simplified the number of rotors that we needed. Also, as part of our hardware, we are using the USRP X300 software-defined radio. For software, you can see we have like a main ground station computer. It has a Linux operating system. We're also using a GNU Radio for our signal processing, and we're using a gpredict-based backend for our website, and of course, a server. I'll give a little bit of context about the communication setup in the spacecraft. So we're using a UHF transceiver, an S-band transceiver, a deployable UHF antenna, an S-band patch antenna, and the reason we're using 2 frequency ranges is to add another layer of safety. So if one fails, then we use the other one. For our modulation scheme, we're using QPSK. And as for our communication protocols, we're using the AX.25 packet protocol. And we're using the ESTTC protocol. That's basically from our hardware provider, which is Endurosat. So now I'll go about how we actually implemented the capabilities that we want into our website. So for the satellite tracking capabilities, we basically looked at the gpredict software, which is just a very popular open source satellite tracking application. We extracted all the graphical elements out of it, and we took just the computational code, which was basically just a TLE processor and the SGP4 orbital propagation model. And we formatted them in a website backend thing, like format. And how it basically works is the backend automatically fetches the most current TLE information for all active satellites from Celestrak every 24 hours. And then the user, through the graphical user interface, enters a satellite catalog number that they want to track. The backend searches for the TLE of that corresponds to that catalog number, and then it passes it through the SGP4 orbital propagation model, and then we get the following outputs that you see in the picture in real time. So the key outputs that we're looking for are the latitude and longitude, because we are plotting those in real time into a map, so we can visually see where our satellite is. We also get the azimuth and elevation values in case we want to move the antenna to follow the satellite. We get the velocity, and then one key component is we get the next AOS, acquisition of signal, which is just the date and time where the satellite will become visible to our ground station. and the LOS, which is when we're going to lose that communication window. GPredict also does the Doppler shift correction for us. So we basically just get the corrected frequencies. So now that we have those outputs that we need, we can go ahead and schedule the communication windows so that our antenna moves automatically without us having to manually move it, and we can establish that communication. So since we now know when the satellite is going to be passing over us, sometime before we can start moving the hardware so that it establishes that link with as much precision as possible. And we basically send the live azimuth and elevation values through a serial link to the communication, from the computer to the rotor controller. And so this is a part of a project that we're currently working on. So this is like work in progress or future progress. Like I said, we're using the USRP X300, and we added two 160 megahertz daughter boards to basically cover the frequency ranges that we want, UHF and S-band. And then how we're planning to integrate the real-time signal processing is that as the USRP SDR is receiving the signals, it's passing them on to GNU Radio to be processed and to extract like the relevant data. And then that data is going to be sent back to our website backend to be displayed on our graphical user interface. This is just what our graphical user interface currently looks like. As you can see, there's a map that displays the trajectory of the satellite. The blue marker that you see is where our ground station is. The white icon that you see is like the satellite in question. It displays like the outputs that I was talking about, latitude, longitude, azimuth. That's all being updated in real time, as well as the future passes. If the user wanted to track another satellite, they would simply click on the button that says Add Satellite, enter the new catalog number, and they would be able to. But yeah, future work, like I said, we want to integrate the real-time signal processing into this workflow of our website application, and then integrate that into our graphical user interface. Thank you all for your time.
Thank you. All right. Stay on stage. I'm sure we have some questions. Or do we not? Wait, there's one up at the back. All right, Mark.
Curious if you were able to leverage any like code or hardware designs from the SatNogs community.
We have been looking at those. They've been helpful resources for us to look at, but I couldn't say like any specific. Kind of just been taking things from everywhere and putting them together.
Anyone else? Okay, I have another question. I know you said this at the beginning, but you know it's like Friday, so my brain is getting a bit slow. So how does this? So you said you were a graduate student, right?
I'm an undergraduate.
An undergraduate student. Wow. So how does and this is basically what, like this project ties directly into your degree, and that's really cool. I feel maybe I went to the wrong school or something, but that is really impressive. I think this looks pretty cool. Yeah, one more round of applause, please, for Adriana. And up next, I keep running away from my schedule. Oh yeah, we have ASU, one more talk from ASU. We have Isabella and Adarsh. Are you both talking? Okay, perfect. Yeah, we don't have a clip mic, so you can just grab that. Yeah, just take turns, and you will be talking about joint communication and sensing, one very hot topic at the moment.
Hello everyone, I'm Bella and I'm here with my lab mate Adarsh, and we're both PhD students in Bliss Lab, so if you went on the lab tour yesterday, you might have ran into our home. But we're here today to talk about some work that we've been doing on joint communications and sensing, specifically using an OFDM waveform. So I should have buttons right here. So here's a quick overview of the topics we're going to talk about today. But as it's been alluded to, this is kind of a hot topic at the moment, but as the number of wireless communication devices continues to grow, and then with that, the radar and sensing application space also continues to grow, there is an arising problem of spectral congestion. And with that, there's a need for smart spectrum management solutions. And one potential solution that people are exploring right now is joint sensing and communications. So using the same frequency band for both radar and comms application, be that switching off or both simultaneously. So the goal of our project and what we're here to talk about today is specifically an SDR-enabled joint sensing and communications platform that we've been working on building, and the results that we have for you today are using an OFDM waveform. So the radar application that we are exploring in this work is specifically human vital sign monitoring. So if any of you were at GRcon last year, I presented on some work using a continuous wave radar built with a software-defined radio that we use to measure heart and respiratory rate. So this is kind of an extension of that work, and there's a lot of very interesting research going on in that space using a small-scale radar system, but not a ton using software-defined radios. So we've had some fun doing that. So a radar or a joint sensing and communications system can be operated in 3 different configurations. So one of those would be a monostatic configuration where you're not using your comms link, but you're just from one single unit transmitting and then doing your radar processing on that specific unit. The total alternative to that would be a bistatic mode where you are transmitting from one unit and then receiving at another unit and doing both your comms and radar processing on that other unit. But the mode that we are working with today is a mixed mode. So we transmit from one unit and then we do our radar processing on that unit, and we do our comms processing on a second unit. All right, so now I'm going to pass it over to Adarsh to keep going.
Thank you. So as Bella was saying, so the interest in using OFDM waveform as opposed to any other comms waveform is just because it's popular, I guess. So if you could somehow utilize it for dual length, that would be nice. So just a refresher course, I guess, on what OFDM is. Basically, you have a certain bandwidth that you end up fragmenting into orthogonal subcarriers, and each of the subcarriers would have a bunch of payload inside it that you end up decoding. We all know that, or many of us know that there are a lot of advantages to the OFDM waveform in sense. It's robust to multipath, better spectral usage, and robust to jamming and interference. Of course, there are some demerits with the PAPR of the signal, but I think we can still utilize that in our favor. So now that we know that, so just another crash course on the OFDM radar. Basically, the OFDM radar operates in a very simple mechanism. That is, you have a transmitter and you have a receiver. The transmitter transmits something, the receiver observes that. And if you just divide one symbol by the other, you end up pretty much canceling out anything that's in the symbol, and then you're left over with some channel component, any Doppler, if it's observed, and the delay of the target, which can be used for ranging purpose. It would be important to note that in this formulation, the delay over there is constant, so it doesn't move, but for our problem, the delay is slightly time varying, so we'll talk about that more in the future. In terms of the selling points of the OFDM radar, pretty much the OFDM radar has low operational cost because you can integrate it with existing systems. So, so there is that to it. And this is where we come to the GNU radio system design. pretty much the system design is kind of off the shelf of whatever is there in the GNU Radio tutorials. You end up having a comms link, which has both timing and frequency corrections to it, and then the radar slash comms transmitter. Over there, we just put a custom payload and then expect it to observe something. So setting this up would probably take a day or two, and it wouldn't be too hard. So now moving on to, I guess, what vital signs are and why is there a lot of buzz in this. So basically, vital signs are motions induced by your body. And two of them which we are interested deeply in are the breathing rate and the heart rate. So every time your chest moves back and forth, as shown in the dummy, it induces some motion, hence a Doppler. The heart rate, though, is more about the pulsation of the heart, so it's not easily visible, but it is possible to deduce that if the radar can penetrate enough. Or it induces motions on the surface. So with that being said, I guess there are some technicalities to using the OFDM itself. So the induced Doppler is pretty much the same for us across the entire spectrum because the motion is so slow that it doesn't really cause too much smearing. We put the subject at close range, so and make sure that they're fairly stationary. And then there's a catch about the subcarrier spacing has to be about 1 order magnitude greater. So in our case, the largest heartbeat possible is it's about 190 beats per minute for the infant, and that translates to about 1 kilohertz in subcarrier spacing. So you can pretty much get away with doing this in very low bandwidth. So for the experimental setup, it is a small budget setup. We have two B210s. One acts as we dub it as monostatic radar, though the antennas are placed about 1 meter away. But they're on the same unit, so we call that as monostatic. And then there's a comms receiver away from here on the other side, which can receive whatever signal is being transmitted from here and decodes it. In terms of the setup itself, it's a fairly long payload sequence, so that it acts more like a pulsed radar. We didn't go too much into the effort of actually trying to put in an industry standard OFDM payload and preambles because the aim of the project was to prove that it's possible more than optimizing the bounds of this. So with that being said, the bandwidth that we operate on is like 1 megahertz or so, and then at this bandwidth, the range resolution is so poor, right? It's 150 meters for every bin that you consider. So, and in close range, that makes a real big deal because you don't really know. You will have a time varying delay that you need to kind of compensate. Yeah. With that said, I guess we'll just go to the comms waveform. Again, we didn't focus too much on the comms link because it's done and we could optimize it further. The comms link is just the standard comms link. There's nothing much we did to it. It has just one sync and a long payload, so we expect the decoding to be bad. There were no, it was not, it had no FEC in it, so it's like, it was bad. But it does, after equalization, you can see that there is some amount of change. So with that said, now the actual fun part of the project, I guess, is that how could you use this OFDM to actually detect this, right? So I think it should play, right? Yeah. So what you see is the observed received waveform at the receiver. It was transmitting, I think, at -5 dBm with a gain of on the RX of 50 dB, so fairly low. And then every time that the heart beats and moves, every time Bella, the subject, moved her chest back and forth, you can see that there's a change in the amplitude, which makes sense. And hence, we can kind of, at least looking at just the waveform, you can say that, okay, there's something interesting happening over there. So with that said, we'll walk through the processing chain that we use for the vital sign recovery. As mentioned earlier, the OFDM radar division has to first take place, so you get some time-varying channel residue. We do some clutter mitigation to remove some background noise that is there. And after that, we do some coarse channel equalization so that the noise is further reduced. The next block is, I call it DC offset, but it's more about the time-varying range offset correction that you do. And after that, the Doppler FFT and an averaging filter so that the noise is reduced. Typically, because we are kind of trying to estimate the beats of the heart in like sub-hertz category, like below 1 hertz. So the phase noise of the phase noise of the radio itself comes into a lot of play, and hence there has to be some way to mitigate that. So I guess these are some of the preliminary results. So on the plot, when you look at the left, the first plot on the top is the amplitude plot of what we just saw. So if I take a running max of whatever signal peak that I get, I can observe that there is some pattern of change in the amplitude itself. That's not too interesting because you can't really deduce anything out of it. However, when you look at the phase plot, you can see that there is some change in the phase, but we don't entirely know what's going on there because there is a time-varying range because it's 150 meters across, and then you don't really know what's happening in between. So you do have to remove that in some sense. So you end up doing something simple, such as a DC offset correction, which would kind of reduce the entire, or normalize the whole value down to what you expect to see. So so the last plot over there that you see is pretty much after the correction. And once you correct that and take the FFT, you can see that there are 3 distinct peaks. We don't know what the first peak is. It could be probably the fan or something, or something slower than that, like a paper moving or something. But the 2 other peaks that are interesting for us is the actual breathing rate and the heart rate, which you can see. Bella took roughly about 22 breaths for that minute. It was pretty hard breathing. But it did identify that, and then the heart rate itself was about 63 beats per minute, so that went good. In terms of the results itself, we didn't actually simultaneously measure it using a PPG sensor or an ECG sensor, because I guess one, it was a small project, so and 2 is that validation would probably require more time. Yeah, so I guess that's the whole thing. So in terms of the project we did and all of that, I guess we operated the OFDM on the lowest bandwidth possible, and then we could still see something. The reason we did that was for multiple reasons. One was because initially we tried to operate these on these small nooks, and we needed like at least a long sequence so that we can get good spectral estimate, and we couldn't process that much on the nooks. So we tried to reduce the bandwidth, but that caused other issues. So eventually we processed it on MATLAB. So yeah, so I guess in terms of the resulting importance of this work is that we could use it in the lowest bandwidth possible. Some future work that we could do is that right now we use just known sequences just as a pulse radar. We could always expect some random comms user to decode the data and then see which would cause more errors, but it's possible. We could also improve subhertz estimation accuracy and use real time for GNU Radio. Yeah, so I guess that's project.
All right, very, very cool. Do you have any questions? Do?
On the previous slide, I'd be curious to see what that graph on the right looks like without the subject sitting there.
Yeah, we don't have that over here, but ideally you would, I'm guessing you would only, ideally I guess you would only expect the first peak to exist, because we don't really know what it is. It's like 5 beats per minute or something, and I'm not sure what oscillates at 5 beats per minute. Maybe like a paper or something, I don't know what it is.
So you have this. You might have the same thing, but then that without the 2 peaks.
Yeah, yeah.
Okay. So what was the bandwidth actually? I know you said it was low, but then I forgot the.
It's 1 megahertz.
Oh, okay.
Yeah.
Interesting. Okay. Any more questions? So I'm still a little bit excited to see my own thesis cited in your slides. All right. Thank you very much. One round of applause. Yeah. And it's actually time for our last regular talk. We have like the CTF results after that. And I am very excited to introduce someone from my own alma mater, KIT Germany. Hey. Yeah, Marcus. We don't have satellite ground stations, do we, at KIT, though?
I don't think we have any satellite things, at least not at the institute where I work.
Okay, but we have other cool stuff. And you're going to tell us about it. Frederick, go ahead.
Are there my slides? Ah, nice. So that's the castle in KIT, in Karlsruhe. Okay, my name is Frederick Ritter. Welcome to my presentation of RSESS, our open source implementation of the enumerative sphere shaping algorithm. KIT is a university in Karlsruhe in Germany, for anyone who didn't know. I'll start by talking about the internet. Works nicely. As we all know, internet data rates are constantly increasing. This means we have to use higher transmission rates, and this means we have to use newer infrastructure, but that would be expensive. So ideally, we would want to operate with higher data rates with the same infrastructure. This means we have to go closer to channel capacity. Luckily, probabilistic shaping offers 1.5 dB in gain if we move from uniform channel inputs to constant Gaussian channel inputs. And this is where we contribute a practical implementation of a probabilistic shaping algorithm coded in Rust, which you can use in research and development. But let's first take a step back and look at the general challenges for probabilistic shaping. So first of all, channel inputs, continuous channel inputs are currently not feasible. This means we will have to bite the bullet and only adjust the probabilities of our discrete channel input signals. Second, data bits are usually uniformly distributed. This means we need a shaper that converts from the uniformly distributed data symbols to, or data bits, to non-uniformly distributed channel modulation symbols. And then at the receiver, we need a D-shaper to convert back to uniformly distributed data symbols. This way, the channel only sees the shaped modulation symbols, and then we get our gain. Next, of course, our channel will never be as friendly as in the picture. We'll always have errors, so we have to use forward error correction. This was solved in 2015 by Böcherer and Schulte with probabilistic amplitude shaping. In essence, this uses the symbols, the signs of the modulation symbols to transmit parity information. For our purpose, it is especially important because this means the signs are used and we may only shape the amplitudes. So there are different algorithms that do this shaping of the amplitudes. Wöcherer and Schulte themselves published constant composition distribution matching, which is a very good algorithm for long block lengths. However, it suffers from severe rate loss for very short block lengths. This is where Laroya's algorithms, they were both published in the same paper back in 1994, come in. They are good for lower block lengths, or what we'll be focusing on, numerative sphere shaping, which is also very good for lower block lengths. It was also published in 1993 by Willems and Witz. ESS doesn't work on single bits and amplitude values, but it maps whole sequences of bits to whole sequences of amplitude values. The idea is to reach AWGN capacity by using the most energy efficient representation of our data. To this end, the used amplitude sequences in ESS have the minimal average energy. And this can be achieved by limiting the energy of the sequences used below an energy threshold. This energy threshold is then also one of the main parameters of ESS. The other two parameters are the number of amplitudes in these sequences and the modulation order, so what order of ASK we are using. So to store all these amplitude sequences efficiently, we use a trellis like this one. Each amplitude sequence is a path through this trellis, and each arrow in this trellis then represents an amplitude. We find indexes for the nodes in this trellis by taking the number of amplitudes it takes to get there, and the total energy of these amplitudes. So just as an example, if we take 2 amplitudes with a total energy of 18, we would come out at this node. By taking this indexing, we have efficiently connected the trellis nodes with the energies of the amplitude sequences, and thus by just limiting the size of the trellis, we can now limit the energy in the used sequences, and thus we can achieve this minimal average energy. The size of the what I just said. We now still need the values. The values can easily be found or are defined as the number of paths from a node to the end. So let's have an example again. We just forget the value of this node, and we can easily retrieve it by counting 1, 2, 3 paths to the end, and then we have the value to be 3. Now these values are very nicely used in the encoding and decoding algorithm. I would have really liked to talk about these algorithms, but there's simply not enough time, so you could ask me later, or you could look at the original paper from Willems and Witz, it's very nice, or you could look at the paper accompanying this talk where I went into a bit more detail. But let's now go on to our implementation, RSESS. RSESS stands for RS, Rust, and ESS is, of course, ESS. It also implements the optimum ESS algorithm published in 2022 by Chen and another Chen. It's especially good for extremely short block lengths. It implements encoding, decoding, so from amplitude sequences to bits and vice versa, and things like the amplitude distribution, the amplitude distribution and the average energy, which is good if you're doing a simulation. You have to find the average energy to do your normalization. We also publish Python bindings called PyRSESS, so you could use these from a Python script or from GNU Radio, Python blocks, or something like that. We published everything to crates.io, that's the Rust package place, PyPI, and GitHub with some examples. It's very easy to use. There's a short example using PyRSESS. You import it like a normal package. PyRSESS and RSESS use a normal object-oriented interface. So we can just create an ESS object with the 3 important parameters: maximum energy, number of amplitudes in a sequence, and the ASK modulation. Then we can define some data, and we can convert this data into an amplitude sequence using the encode method of ESS. We just get a sequence of amplitude values. Then we can play receiver and use the decode method on the received sequence, and of course we get back the normal or the bits we put in. This is of course a very simple example. We could do much more. For example, normal simulations will entail many, many more transmissions. So what we did is we simulated or measured the time for 10,000 encodings or decodings. We also kept the shaping rate constant so that we could compare different amplitude sequence lengths. Shaping rate is the number of bits transmitted per amplitude. And we tested all of this on an i7 from 2017. You can see the length of the amplitude sequences on the x-axis and the time for one call of the encode or decode method on the y-axis. And first thing we can notice is that ESS or PyRS ESS, the Python version, is the dotted lines, is slower than the pure Rust version. I don't think this is surprising, as Python is just slower, and also we have to always convert data rates if we're using Python. So that's not really surprising. Another thing is that encoding, the blue lines, is slower than decoding. That's just because the algorithm is more complex. In general, we can see that all execution times are below 1 millisecond, which is already pretty good, in my opinion. If we keep in mind that RSESS main advantage is its very low rate loss for short block lengths, we should know that it's usually also used for short block lengths. So if we look at block lengths below 500, we see we are even below 200 microseconds, which would be equivalent to 5,000 runs in 1 second. We also ran some memory benchmarks. Once again, PyRSESS is less efficient than RSESS. I might want to mention that these benchmarks include the base process plus the energy or the space required to store the trellis representation. PyRSESS is still very much efficient if we look at shorter block lengths as what ESS is usually used for. So we are still below 50 megabytes, so that is very much usable on any normal hardware. If we want to use extremely long block lengths, we can use a pure Rust version. It's below 40 megabytes all the way to the top of the plot. So this wouldn't be very useful if we couldn't do some real simulations with it, which of course we also did. We could even reproduce some results from literature. On the right-hand side, you can see a plot in the paper from Chen I mentioned earlier that published optimum ESS for the very short block lengths. It has SNR on the x-axis and the achievable information rate, so how much information we could theoretically achieve on the y-axis. And the most important part of these plots, why I'm showing them, is because our results are exactly the same as Chen's results. And this means that our implementation works as expected, which is very good if you're publishing a library. So I hope I could interest you in non-uniform transmission schemes to increase data rates. And I published or introduced our implementation of ESS called RSESS. It's relatively fast because it uses Rust, and the results we get using RSESS match results from literature. I hope if any of you are in this field that RSESS may be useful to you. Thank you for listening, and I think there is still time for questions, so feel free to ask.
All right. Questions? Oh man, his hands are going up left.
Thank you for this talk. My question is, in the last slide, you showed the achievable data rate, I guess. But how did you found it in the real implementation? How did you compute it?
In this case, I would propose you look at the paper by Chen or the paper where they got it from. I'm not sure. It's a very nice way of taking the received signals before doing the error correction. And if I remember it correctly, you kind of take the distances between what you would expect and what you receive and the log likelihood ratios. And then there's a nice formula, and you plug it in there, and then you get these achievable information rate estimates from it.
Yeah, thanks also from me. This is all the real case, right? We're just doing on one axis the amplitude shifting and...
Yes, the simulations were all real, but as it is completely, well, you can just do the whole same thing on the imaginary axis, then you got the QAM modulation. So these plots are showing the achievable information rate for QAM modulation.
Does that work? Because like if I do like maximum amplitude on I and maximum amplitude on Q, I don't get twice maximum amplitude, but I get like, you know, square root of 2 because it's, or I get 2 squared because, you know, energy goes quadratically with distance. Pythagoras and stuff.
Yes.
So then...
Well, you do get different amplitude in total, but you should just be able to do both.
Okay, I mean, if you say it works independently, that's super cool, because then we just get twice the data rate, right? So
Exactly, we just get twice the data rate.
Nice.
It wouldn't be this nice analogy between the amplitude and so on, but I think it should just work.
Yeah, okay, cool.
Yeah.
Thanks.
All right. Any more hands? Okay, in that case, thank you, Frederick. Thank you. Now we're almost at the end, and I think I don't know. I can feel the 4 days of conference. I don't know about you guys. Well, it has been easy going, but I do have to say I've been to conferences where I was falling asleep despite having plenty of sleep, and here it's the complete opposite. I'm totally sleep deprived. But I've been listening to talks all day, and they were all really cool, and I just wanted to listen. So. Thank you very much. And I guess this is my way of saying I would like to thank all the presenters and speakers one more time for presenting like a really jam-packed, really cool lineup of talks like across the board. We had so many different topics. It's open source and space and academia and research. It is all there. And hobbyists. This is one of the few conferences where you have all of this. So I'd like to get one more round of applause for all the speakers for providing such an excellent program. Okay, and that almost concludes like the sort of the main talking track. Of course, we'll still be here tomorrow doing more hands-on stuff, but we have 2 more things for today. And of course, first of all, Clayton will talk about the results of the capture the flag. So I know there was a couple of you guys hacking on. Who did any capture the flag stuff here in this room? There's a couple of teams. There's one here. Yeah. Yeah. Nice. I did not. I did not have the mental bandwidth also. I know. You say that every year, Sam, and then I never do. Do you wanna plug in your laptop? I'm just trying to bridge time until you're ready. Really. Yeah, capture the flag, really cool. It's also really educational. Was it fun? Right. What specifically? Oh yeah. So tomorrow Clayton will actually show some of the puzzles and stuff like that. But yeah, for now we just want to see who won. That's really all we care about.
About to find out. Okay, here we go. Looks like my machine is up. So, capture the flag. You've been hearing me talk about this all week, and we've finally reached the end just about 5 or 10 minutes ago. So let's have a look at how things went. We had a total of 120 players register. 60 teams scored at least 1 point on the scoreboard, which is an impressive number. In total, we had, I think, more challenges than we've had in any previous GRcon. We had 75 challenges, and if you'd solved all of those, you could have earned 4,754 points. So that was a lot of things that went into the competition this year. In all, we had 947 correct submissions and 1,955 incorrect submissions. So lots of people desperately trying to earn their points and putting in anything that looks like it might be a flag. So, without further ado, let's see who the winners were. And we'll start, drum roll please, we'll start with our third place, Andro Computational Solutions with 2,349 points. Is anyone here from Andro team? Okay, I guess they were entirely remote, so let's congratulate Andro Computational Solutions once more. All right, and drum roll please for second place team. Caliola Engineering LLC with 2,888 points. Who do we have from Caliola here? Come on up. All right, yeah, so last year, Caliola Engineering was a team of one, just Vlad. And this year you brought some friends with you, did very well once again. So, yeah, we have a challenge coin and some prize bags for all of the winners. So congratulations again to Caliola Engineering LLC. And drum roll please for the first place, Aerospace Team Platypus with 3,494 points. All right, who do we have from Aerospace here? One up. Congratulations. All right, so with competition over, the CTF isn't quite done yet. So tomorrow at 2 p.m. local, I believe it'll be right here, that's 2100 UTC, we will have various competitors presenting the solutions to their challenges and showing off some of the weird and wild signals that they encountered this week. And so that'll be here. We'll be online. I believe we'll be using Big Blue Button, so remote participants should be able to join as well and present their solutions. We will try to get that presentation recorded and posted to YouTube as well. We also have source code available. All of the challenges that I put together are on my GitHub, argilo/GRcon23, and I know a number of the other challenge creators also plan to publish their solutions. So look for the links to be published in the CTF channel and also on the CTF homepage, which is ctf.gnuradio.org. I'll be getting those all up over the next few days, and anybody who writes a blog post, I'll also link that so you can check it out. I'd like to thank all of the individuals and teams that contributed challenges to the competition this year. Danielle Estevez created a great DVB S2 track that people had a lot of fun with. Aerospace Corporation put together a very nice challenge track with a backstory and all kinds of different puzzles for people to chew on. Vlad Fomichev put together a very nice NRSC5 HD radio track that had 17 flags in it. And Jeff Long put together some fun analog audio stuff with a little bit of digital mixed in, which was a lot of fun. So thanks to everyone who helped create challenges, and we hope to see you next year in the CTF.
And of course, thanks to you for organizing and running this. the CTF is certainly one of those things that GRcon, I believe, has become known for, and that many of the regular people find a highlight of every year. It's something that I find a highlight the week after the conference, is getting to try out some of the challenges. So thank you very much. I think we do have some slides for the end. Nope. All right. Josh Mormon has tapped out for the day, as I think some other people have. He's hopefully resting well at the moment and will be back tomorrow. Busy from all of the GR4 conversations. Martin, did you want to say other things as well? I just want to. Okay. Yep. We'll see how much we can double up on our gratitude for the community then. Organizing the conference is always a lot of work for everyone. So special thanks to Sam again for leading up the organizing this year. Josh Mormon was also heavily involved. To our ASU hosts, thank you so much to Dr. Dan Bliss, to Brittany, to Lonnie, to Julianne, who all stepped in and did a huge amount of work over the course of the year and right up until the last minute in supporting to that. I'm sure there's still some wrap-up left to do. We have Barry, Mark, you know, Toby. The trying to enumerate the entire list of organizers is something I would have to pull my phone out and go down the entire list of chat to correctly enumerate, because this is definitely a team effort. Sorry, I'm wandering away from the camera here. It's a team effort that requires a lot of people in and out. Not everyone's even on the main organizing chat. There's people who jump in, contribute challenges, people who support online, etc. So that's great. We unfortunately do not have a venue to announce for next year. Where there is smoke, there's fire, I hope, and so we have several smoke signals. We're hoping to be able to nail down at least one of those and be able to announce next year's venue. The idea is certainly to do that by very early next year at the latest. I will let everyone know as soon as we have an address and hopefully a date. So we will be continuing tomorrow with a bunch of hands-on activities, the CTF solutions, discussions of GR4 architecture. There's a rumor that there'll be a whole bunch of folks coming in with questions about Cubesats. So if you have, questions about GNU Radio, your own applications, little projects that you've always wanted to work on, but might need a bit of assistance on or a second pair of eyes, tomorrow's a great time for all of that. We have the alumni ballroom that the expo hall has been in, and then we have a new room that's down at the end of the hallway. I won't try and remember the name of it. I believe it's Pima. Grand. And we'll have the registration desk, so if you can't find things, definitely ask there. We are starting at, we don't have the registration desk. Great. We're starting at 9. I should have pulled out the schedule, but look at the schedule. It has the information for that. I won't try and second guess the authoritative set of information and mislead people. There is no official social tonight, but it's a great night to go out with for dinner and etc. All of us do need to eat. So something I would say is, if you are here solo, or if you are here as a first-time participant and hopefully have met some people but would like to meet more, we are ending about 5 o'clock, probably a little bit early. Well, I guess half an hour early at this point. I would invite you to form groups to go out to dinner, find some people. If you're solo and interested, let's gather outside the registration desk. I would love to find some people to get some food with and just chat. So thank you very much. I'll get Martin up for anything else that I've missed. And it's been a great day.
You're saying we should ask people to help break down the room? All right. For everyone who's not yet starving, it would be nice if you could help just move out some of the things. I don't know exactly what I'm guessing we have to move. The power cables, we need to go there also, if you can just help with that. But whatever you can want to do. But Derek, you did forget someone important. That's why I'm coming up, and it's yourself. Can you please come join me on stage one more time? We said it at the beginning of the conference. Derek was, so we had this effort to sort of more formalize the structure of the GNU Radio organization. And so we had a great bunch of benevolent dictators over the years. You know, Eric, for example, kicked it off. Tom added like a whole bunch of things like the conference, and then there was Ben Hilbert. And what came, like the next step of the evolution at the time was a more formal structure where you had, you know, actual rules that were written down. And in those, in that structure, Derek was actually the first, and currently, yeah, the first president of the new, of the newly formed sort of restructured GNU Radio organization. And we said this at the beginning, his term ended just recently, and technically it already ended last week, but I feel like GRcon is really the point in time. And I was actually going to have Josh here, because he is now the new president of the project, to sort of hand the baton on, but he's passed out, which is totally fine. I hope he gets some rest. But still, Derek, you've done so much work over the last 3 years, and I know you're going to be sticking around. I know you're not leaving, which I'm very, very grateful for. I don't think we could do this without you, but I just can't express how, you know, how grateful I am, and I think the same goes for many other people. The amount of work you put in, not, you know, just not the hours, it's also like the passion you've shown, and the great ideas and the patience you've had with everyone. And, you know, the conference also is something that, that has benefited a lot from your time, energy, and just your, you know, general personality, or usually in a good mood, and hard to hard to wear down. And yeah, so in as a representative of the, you know, basically for Mark, Josh, and also the entire rest of the leadership and the entire community, I want to thank you one more time. And I would be really appreciate it if you could, you know, give Derek a huge round of applause for that. Thank you. And that is actually it for the main track. So yeah, of course we will, like Derek said, we'll be back tomorrow, but in a more informal setting. All right, bye bye.
I guess if I'm outgoing as president and no longer officially bound by being responsible, I'll take 2 seconds here to say that my PhD ends in a month and a half, and I'm hireable.